laid back. If you're any more laid back, you'd be asleep, wouldn't you?
Well, we normally get Blue to come in here and sleep on stream for us.
Well, we finally
I had a story.
we finally made it. There was a few technical hiccups, and somebody was touching the wrong buttons and had a few problems. But thankfully,
Somebody.
Who was touching the wrong buttons, Terry?
Alan sorted it all out.
Alan. Anyway,
It's all fixed now.
I had a story for today.
And all that distracted me from what I was meant to be doing. What's the title of this one called again?
Pressure.
Pressure gradients.
No pressure. No pressure.
Proof of pressure gradients.
Okay.
I had a little look on about pressure gradients, and I couldn't sort of find anything that was easy. To, like simply put, it was all really, some of it went into real technical stuff, and I'm sort of going, oh my God.
I found a PDF about it with pressure gradient and gravity and stuff, and I looked through it, and it had all these formulas and everything. And oh shit, I'm not going to try to work that one out.
Yeah, that's about where I got to.
Terry, play my video.
I know what.
Play my
Peter
video,
made-
Terry.
If I got it handy.
Peter made a video. Peter made a video, did he? Did you, Peter? You made a video? Did
yeah.
you? Did you?
A while ago now, actually.
Did you?
Oh,
I didn't know.
Have you got it handy?
In about, give me 5 seconds.
I was trying to look up what
One.
clouds could relate to.
2,
Maybe, hang on.
3.
No,
4.
Google's not playing the game.
There we go. Lots of pressure without a container.
Yeah.
Loads and loads of pressure without a container. Oh, and some horizons.
Careful now. You can't debunk them all just in one go. You got to spread it out.
Yeah, okay, farmers. Look,
There you go.
and please use my new name.
Grandad.
The plain truth.
Oh, the plain truth.
As in aeroplane.
Crash has already took that.
Just remember to turn the sound off on it, Terry. Because it's noisy.
Well, everything should be working as it used to, we hope.
Oh, where's my mouse?
Oh, that video, I remember that one, I think. Have we seen this before? I don't know, I might have done.
Well, that gives you your pressure gradient.
Oh, yeah.
What, you mean that thing that's impossible if there's a demo?
Oh,
Exactly.
haven't you seen this video, Farmer's Boy?
No, I don't think I have.
Farmers, technically, if the thing that stops the pressure gradient inside the dome is the fact that they also deny gravity.
Well, yeah, but if there's a dome,
because
we're
you
in a
can get
container.
if you have a big pressurized container, right, and you leave it to stand for a long time, it will still generate a pressure gradient across it because of gravity.
Now, that brings me to the point. The airplane that does the 0G, for the astronauts and anyone who goes in the airplane. What does the G
vomit.
stand for
Vomit
in the plane?
Yeah. But also as well, the other thing as well, if they again insist on a dome, then the sun has got to be outside of the dome.
No,
got to
well,
be.
it can't be because an expert says it's only 4,000 miles up.
Yeah, well, that's the thing. If it's inside the dome and it's a sealed system, what's going to happen to the gases when the sun heats up all the gases?
Well,
They expand, right?
More to the
We're not
point.
dead yet.
more to the point, Casual. If the sun's on the inside of the dome, if you could imagine this, a fish tank with a sealed lid, and you light a candle inside that fish tank, imagine that candle is more of a, say, we'll call it a Bunsen burner that's got a never-ending supply of fuel. that fish tank is going to heat up.
Yes.
It will get to a point that that fish tank gets to the same temperature as the sun because the heat can't escape.
Yeah.
You know,
Exactly. It's another thing. Yeah, absolutely. Yeah, absolutely. But apparently the answer I got when I was on Jose's show as well was the moon cools it all down. Oh,
But-
right.
no.
I thought the moon heat things
Well,
up.
that's what I got.
Jeez.
That's the response I got.
Fuck.
I keep playing your video, but you haven't
Yeah.
said nothing, Peter.
Oh, sorry. So this is a practical demonstration that you can have two different pressures right next to each other without a container.
Yeah, where's the membrane that's separating them?
There's no
That membrane that must be well everywhere
so
all at once.
all I did for those that are out in the crowd.
You haven't said nothing, Peter.
Oh, Alan's playing back for us.
Yeah.
Sorry,
All it is, it's an air pump that's pumping about, I think it's something like 400 liters a second. A minute.
Say 400 liters a second is going.
No, 400 liters a minute. I think it is. So it's maybe just a bit stronger than, say, your extraction fan that's in your bathroom to suck the steam out of your bathroom. However, it's coming out of a nozzle, so it's actually all contained within a small area. And I'm just moving my watch, which has got a barometer and an altimeter in it, out of the airflow and into the airflow. So as it goes into the airflow, it's confusing both the barometer and the altimeter enough to make it think that the air pressure is going up. Hence the barometer goes up, and the meters above sea level acts as if it's going down closer to sea level.
The lower you go, the higher the air pressure.
Yeah. So it's just you can do exactly the same experiment at home with, say, a hairdryer, and it's the same principle that when you get a straw in, say, a drink, and you blow across the top of that straw, it will draw the fluid up through that straw and spray it against the wall or wherever you're facing. It's the same principles. It's the same principles from Alan's photos of the condensation on the leading edge of the wing, on the trailing edge of the wing. It's these principles are something that happens every single day, and as much as they like to deny it, there it is. It's fact. You can record it. You can do it. You can do the experiment. You can prove it. They're wrong. End of story.
But they're not going to do that, are they, Peter?
Oh, no, because it wrecks their narrative.
Of course it does.
I don't like doing experiments.
No.
And the ones that do them completely wrong anyway.
Because numbers don't matter.
Eggs, anyone?
These numbers could be unicorn farts.
And I was about to tell you a story about yesterday, because I went out to the beach where I live, and beautiful, gorgeous blue sky. The sun was about maybe 35 degrees above the seawater, and the moon was shining at the same time. Thinking, how does that work on a flat Earth? Yeah. And then a dolphin swam past me. Oh, that was cool.
What'd you ask the dolphin?
Is the Earth flat?
The dolphin said, "So long and thanks for all the fish."
That's right.
What about the white mice?
What? Was it Benji? Was it Charlie and Benji Mouse?
I can't remember.
I can't remember either.
Been a very long time since I read the books.
they're on my Kindle along with 3 million other books. So I'll get round to reading them again one of these days.
I'm sure I have the paperbacks around somewhere if I, unless Rosie's thrown the bloody things out.
Sacrilege! Burn the heretic.
Oh, I know.
Stone her!
She's a witch.
Love books, proper books, real books.
Yeah, I've got one or
People,
two.
paper.
But yeah, this whole thing. I mean, just the sheer fact that we have a pressure gradient just destroys so many of their. And I hate to do this. You can almost hear my fingers moving. Their theories.
Mm.
Well, I was looking
Cool.
at the for clouds, for pressure gradient and gravity, and how that all relates to different pressure gradients with how clouds are formed, and I can't even begin to where to start with the explanation.
Well, do you know one of the biggest and most obvious giveaways is when you see a thunderstorm in the distance, and the thunderstorm cloud has what they call an anvil shape, in that the higher it is, the more it spreads out, and it stops at a certain point. Why does it stop at a certain point?
And
Because there's not enough air pressure there for it to maintain itself. That's why you get that sort of anvil, or it's not a mushroom because that's a totally different cloud, but it's like an anvil shape, but it goes up and it curves out, and it
with
generally
that
forms a flattish top to it, and that's because of the pressure gradient.
and with that, Farmer's Boy, quite often they'll be actually dead flat underneath as well.
Quite often, yes, and that's to do with pressure gradient too.
Yep. And
and I'm sure this is why, one of many reasons why they say you can't tell the shape of the Earth by looking up at the sky. Well, you can, because as soon as you look up the sky and you start observing all these things, it just proves that everything that they're saying is, in using technical terms, bollocks.
well, no,
We've been watching CHL again, haven't we?
Farmers Boy.
Look, we're English. It's what we say anyway.
I think.
I know.
I think correctly it's when they say you can't look up at the sky and tell what shape the Earth is. What they really need to say is, I can't look up in the sky and work out what shape the Earth is.
Yeah.
Because
no,
it's not that people can't do it, because, look, clever person, a calculator, a slide rule, a piece of paper and a pencil, a couple of bits of a protractor, a compass, and a few other bits and pieces, and you can quite easily work out what shape the Earth is. The problem is they don't have
they don't have, though. They don't have those type of tools.
Well, the biggest tool that they're missing
is brains.
Yeah. And the ability to use it in a way of working out the math and understanding it. That's where the problem is.
Or math. They don't know math, do they?
Oh, now you're talking the dark arts.
Has he got a cloud in the bottle there, Terry?
Yes, he does.
Yes, he just made a cloud. That's how clouds are formed, by how they reach lower pressure. There's the water, the heat rises to take the water vapor up higher.
Yeah,
he
basically just reduced the pressure in the bottle, didn't he? And now he's pumping it back in. Yeah.
That's an experiment. Oh.
Which is exactly why when you get the aircraft doing the high delta maneuvers, the jets, when you see the clouds of vapor on the wings, because they're able to drop the pressure enough that the vapor condenses out.
Well, even more impressive is when a Formula One car can do it. Coming off the tips of the tail spoilers. If the air's damp enough and they're going fast enough, they'll form contrails.
And even on your standard commercial flight. Excuse me, sorry about that. Oh, I must be getting the flurfies. Even on your standard commercial jets or your commercial jet planes, you know, they may not be going so fast that they get the air all the way along, or the cloud forming all the way along the edge, but quite often at the very tips of the wings, particularly when they're the style of wing that's bent up towards the tips. You know, right at the tip of that wing, you'll quite often get
you'll see it. Yeah.
a cloud forming at the edge of that.
Yeah.
Yeah,
You've got to get, as long as you've got the right temperature, the right pressure, at the right altitude, you will get contrast.
Well,
Hey,
more
you mentioned
importantly,
Formula One
humidity.
cars previously. What keeps them to the ground? Density or buoyancy?
Yeah.
Aerodynamics.
Yeah,
and
they're pushing
downforce.
themselves down.
They
Yeah,
are most
air
definitely
pressure.
pushing
They
themselves
are,
down.
they are basically
Exactly.
an upside down wing.
Yes.
Air pressure,
That's
push it
it.
down.
Actually,
rather than
no. Actually, no. It's not air pressure pushing it down. It's lower pressure under the car holding
Sucking
it down.
Sucking
Oh,
it
okay,
down.
all right, okay.
It's the same with the wing. It's not
You
the
keep-
high
you keep
pressure
correct.
under the wing pushing it up. It's the low pressure above the wing pulling it up.
Which is why back in the day they experimented with side skirts.
Yeah.
And
Yeah,
they
but what I
found
mean
the
is
cars
that
were going too
there's
fast.
still a higher pressure underneath the wing compared to above the wing, though, isn't there? Really?
Yeah, but it's the but what's actually doing the lifting is the lower pressure, not the higher pressure.
Right,
It's-
okay.
It's the difference between velocity pressure and static pressure.
Yeah, but the whole idea is to explain higher pressure outside of a container, isn't it? So you can say,
Well,
there's
no,
higher
actually-
pressure underneath the wing.
No, because the differential pressure is the low pressure above the wing.
Yes.
Pressure
Yeah,
under
no,
the wing
I
is just
understand.
is just whatever air pressure
understand
you
that.
happen to have.
Yeah, I understand that, but what I'm saying is that what we're talking about is having a high pressure outside of a container, right? But the wing is still creating a higher pressure underneath the wing, and I understand.
No,
Yeah.
Hold on. It is not. It is not. There is no high pressure.
Okay.
There is only a low pressure.
Okay.
Okay.
Hmm.
I had a question for Mippet.
Yes.
You mentioned you went up to do your parachute jump.
Yes.
Did you see the curve when you did it, and were you able to breathe?
I actually jumped from 17,000 feet, and it was a cloudy day. So I got told to shut my mouth, or else I get grit in it as I jump through a cloud. I did see the opposite peninsula, so over to sort of Port Lincoln. So I saw a long way, but no, I didn't see the curve. I wasn't up high enough for sure.
Yeah, no problems there.
No,
I mean, that's,
17,000
we're talking about the pressure,
feet.
though. You're up there high enough. We saw the Red Bull, what was it, the German guy? I can't remember. The guy who did the jump from some astronaut.
Felix Baumgartner.
That's him. Yes, his using a spacesuit and everything, and jumping from there is huge way away. But you needed oxygen in your own suit to do so.
Yeah, well, he passed out on the way down, didn't he? And then sort of came back.
Did everyone know that there's another guy that's already beaten that record since then? A guy from Google.
No.
Did you know about that?
No.
I'll give you the link. Hold on. There's a guy that's beaten that record since then. Hang on, I'll show you.
But Baumgartner was basically replicating something that was done in the early 60s.
Yeah.
By no means the first guy to do it.
I think he was just the guy to go highest at that particular point, wasn't he?
Yeah, there was an American chap who did it sometime in the early 60s. And
yeah, it was, but the Baumgartner beat his record. That's what we're saying. But since then, there's another guy that's done it in an even bigger spacesuit, almost pretty much like a pressurized container is sitting inside, and he's broken that record. I'll show you then. Hold on, let me see.
How did they get up so high? That's what I want to find out.
Well, while you're doing that, Casual, while I was googling all this air pressure and clouds and what effect gravity had on air pressure and that, I found an older video with a flat earther, and I'll play it. And you can.
Flat Earth Proof 28. The clouds. Have a look around on any semi-cloudy day and take notice of the clouds further away, near the horizon. Notice particularly the bottoms of the clouds, how they all seem to form a straight line, level in the distance, parallel to the horizon, all the way around you. Not only do the clouds not appear to curve from side to side, increasingly so the higher you go.
I have to watch out for the music playing in the background. I'm not
Terry, could you pause for a second? You know, he was just talking about how far away, when you get the clouds out near the horizon and they still look like they're flat.
Yeah.
Well, the thing is that that's exactly what you would expect on the Earth. Because if you've got clouds at 2,000 meters, when you see them when you see those clouds eventually touching the horizon, those clouds are 160 kilometers past the horizon you are looking at.
Yeah.
So, however, at 2,000 meters, it's 160 kilometers. Or if you prefer it in freedom units, it's 6,600 feet and it's 100 miles past the horizon. So whatever your distance to the horizon is, when you see the clouds at that altitude coming down level with the horizon, they are 100 miles, 160 kilometers past that horizon. Well, that's only about a degree and a half. So it's not like they're going to be tipped over and you're going to be looking at the bottom of, is it? Quite. You know, it's actually surprisingly how fast, with altitude, how far stuff away is quite surprising sometimes. It's the same with aircraft. They do tend to be quite a lot further away, but even then, it's sort of the highest commercial aircraft are only ever going to be up to 450 kilometers away when they curve around and reach the horizon.
Yeah.
So it's still only a few degrees. And I challenge anybody to notice an aircraft change its angle by 3 or 4 degrees.
You'd be hard pressed to. It's like, you know, if you had a sufficiently tall enough building that's 69 miles away and you can still see some of it, there's no way that you can tell that it's leaning 1 degree away from you. You just can't. It's not possible.
Can I play?
Yeah.
Side to side, increasingly so the higher you go, with a fisheye horizon being the norm. But on a ball, the clouds would additionally lean over, falling over the horizon, which is allegedly where the curvature of the supposed globe is said to begin, thus allowing you to see their flat bottoms meeting the line of the ground. Of course, it's not that way, with deniers resorting to such justifications as, the Earth is just too big to notice any curvature, derp. So, if the clouds don't curve, when the sun is setting, supposedly at 90 degrees to the observer on a ball, the clouds should demonstratively be illuminated from their underside, their dark portions on their tops. But instead, clouds will only appear.
I thought you should get a kick out. I knew you should get a kick out. That's why I was waiting for to play it. Because I'd already watched it. It only goes for 2 minutes, and you just wanted to stop it that early before. But I had to let it play.
Had we known such comedy gold was coming. You know.
Yes, yeah, if I'd have seen it, I would have waited and done the,
I was trying to not let you
done that whole
pause it.
thing right at the end.
Yes.
Yeah. Okay.
10 points for that one, Terry.
Nice. Right.
There's more.
Clouds being illuminated underneath.
Yeah, but
Hang
wait,
on, go
there's
back
more.
and do it. Go back and do it again.
Just that bit. That I know it's gold. That bit. Just after there.
Yeah, let's let it run from that again, because that's just.
You listen.
When the sun is setting, supposedly at 90 degrees to the observer on a ball, the clouds should demonstratively be illuminated from their underside, their dark portions on their tops. But instead, clouds will only appear in.
Now we can see underlit cloud here.
Yeah.
Just rather a lot of it.
Just wow.
Illuminated from above or from their sides, whilst twilight fades out around the setting point of the sun and not evenly across the western sky, as would be expected on a ball. So investigate the subject for yourself and ask questions.
We have. It's not flat.
It's amazing.
This guy brought
who the
this
hell
out.
is it?
Says, oh
Terry,
God.
Terry, who is he?
I'd like to
know the Earth. He's got
Know the truth.
4.5. Yeah, know the
truth.
truth. 4,500 prescribers. He brought this out in February 2017.
Again, it's typical sort of flirt. I mean, like he's saying something, but he's not actually citing or demonstrating or proving what he's actually saying is true, as always. And people are fall for it again. He's just telling people what it is, what he thinks it is. Well, what he believes he knows it is.
And I think he's just doing it. I'm pretty sure that is actually Dubai's number 28. So I think he's obviously just doing the debates.
Yeah, well, this is 2017, so that's
back in the thick of it. That's right back in the thick of it. When did Dubay do his 200 proofs?
A while ago now.
Yeah.
But the joke is that if that's a Dubay number 20 whatever, that's also a Dubay number something else.
Yes.
Something else.
Yeah.
He does have a habit of repeating himself somewhat.
What do you want more of him?
Well,
I've got these few that are
go ahead, Terry. Another one. That was funny.
If they're the same sort of comedy gold, then I think we ought.
He's got either. Why can't people accept the flat earth truth? Who's got problems with their audio?
Yes.
Not me, I think.
Not me.
Can I quickly share something, Terry? Just quick. It only take literally just a minute, if not.
Do I need to have my vaccine before you share it? I only just found it when I was just googling all the pressure gradient, gravity, and clouds, and that came up the first video. And when I went to it, then went to his channel, and I went, "Oh, how come I hadn't heard of this bloke before?"
Yeah.
Yes, Irish. I think that was probably produced by Ranty.
Yeah.
Or at least Ranty probably told him what clips to get, clips to use to do number 28.
Here, use this because it disproves what you're claiming. Oh, and I should know because I do that every time I create a video.
Yeah.
Yours, Ranty, the globe.
So nice how they keep proving the globe, don't they?
Ranty's an expert at it. Of course, the joke is that he strenuously denies proving the globe Earth.
And Laurie says there's definitely some questions to be asked after that video, and Stewie says, like, why bother?
Why bother?
Right, here it is. This is
come on then.
Alan. This is this guy, Alan Eustace, who beat Barn Gowder's record.
Somebody's got problems with their mic. I can't.
I'm not gonna. I'm gonna play the video, but I'm not gonna. Oh, that's horrible noise.
Oh.
Wow.
I'll play the video, but there's no.
It was Miffit.
Yeah, it was Miffit. Yeah, I'll play the video, but there's no audio. I'm not going to play the audio or anything.
Okay.
So he's like attached in his. If you can see there, he's attached to his to like the balloon in his actual suit. It's pretty much like was like a metal suit almost.
Now that's very similar to the first guy back in the early '60s, because he wasn't in a capsule. He was basically just sat on, something attached to the balloon. Yeah.
So he was released. So Baumgartner's record was 128,000 feet, and he did 135,000 feet. Not many people know about it. I'm surprised.
No, this is the first I've known of it. It's not been very well publicised. Certainly not as publicised as Red Bull.
And all this guy is he's like an analyst or something. He works for Google. That's all he was. He wasn't a skydiver. Well, he is a qualified skydiver. But he's not like a professional pilot or anything like that.
So presumably he broke the speed of sound as well.
Yeah. Yeah, absolutely.
Which I think, sod the height, sod everything else. The fact that you can go so high and fall so far and so fast that you can break the speed of sound yourself without being inside an aircraft and going, buffeting,
Yeah, exactly. So I don't know if you can. You probably can't. Can you see that screen where it's got Alan Eustace?
Yeah.
So Alan Eustace,
35,890 feet.
Yep, and then there's Baumgartner's 128,000 feet. There you go.
Yeah, well, I guess Baumgartner had all the, it was all Red Bull sponsorship and everything else.
Right, I can't seem to be able to stop sharing. Where's the button gone for stop sharing? I can't see it. It's gone.
At the top of your screen, the little green bit that comes up when you put your mouse at the top of the screen.
It's not there. It's not doing it. Hold on. Oh, there it is. It's appeared at the bottom when I closed everything down. There you go.
There you go. Yeah. 135,000 feet. And people will still be saying, did you see the curvature? Yeah. Because, you ain't getting a much wider field of view than the helmet of whatever spacesuit you're wearing.
And anyway, I saw an explanation. What you have to remember is that as you go up, even when you're standing on the ground, you see a circle around you.
Of course you do.
Past the distance, but you're looking at it because you're not looking straight down on that circle. You're looking at it obliquely.
Yeah.
So it will appear to be oval.
Also, Terry, as well. Sorry, go on.
So if you do that, squidging the image together sideways, if you've got a fairly wide bit of it, it will have an apparent curve simply because of the geometry of looking at a flat 2D shape from slightly above, where your field of view can't encapsulate the entire thing. You'll see a bit of curve if you then squeeze it together. And that's different. That's what you see when you get up in things like the U2 or in these balloons, is you see that effect. I think that's even the same effect you see when you're in the ISS. I don't know that the ISS is actually high enough even to actually see any part of the Earth as a disc, but as the disc.
They still only see quite a small part of it, don't they? Quite a small percentage of the Earth.
They're only 200 miles, 400.
But just to put it into perspective, he's still nowhere near what we would call space. 135,000 feet is 41 kilometers.
Yeah,
that's not even halfway to the Kármán line.
Well,
no.
It depends on how you define the Kármán line. If you use Kármán's original definition, that was 86 kilometers, which is the point where a wing, where you would have to have orbital velocity in order for a wing to produce lift.
I
mean, there are two now. It depends on whether you go by the FAI or the Yanks.
Which is 100.
Yeah, the FAI is 100 kilometers, and the Yanks say 80.
Yeah, the only reason why they changed it to 100 was because it's just like a round number, really, and it was just simpler for people to grasp hold of. That's the only reason, really.
62 miles, 330,000 feet. So he was, just over a third of the way there.
Yeah. I mean, that's what gets me. I mean, I always like to think of like the same thing as Alan said was 86 kilometers. That's really the point that space kind of begins, really. And as Alan said, you can't get any lift with any kind of wing.
No, you can.
Hold on.
Actually, you can get lift. It's just that to get the lift required to support a body, you would have to be going at orbital velocity.
Yeah.
So it makes the wings superfluous.
Yeah, but again, it's still, when people actually sort of say that they've gone into space, they did a near space jump and all the rest of it. No, it's not. I'm sorry, but it just isn't.
Nowhere near, I'm afraid.
Nowhere near. Yeah.
It might be very, very high, a bloody long way up, but no, you ain't even.
I mean, it's the same. It's the same with balloons and all the rest of it. I mean, most balloons only go 100 to 120,000 feet, maybe at the stretch 120,000 if they're lucky. Yeah. Most balloons, it's and this business about balloons being, all the satellites being on balloons is nonsense.
Wow, it's
for that very reason.
It's a display of ignorance, I'm afraid.
Yeah, of course it is. Yeah. But anyway, we're going off topic.
Oh, I don't know. It's atmosphere pressure and gradient. Sure.
Yeah, true.
Indeed.
But Terry, I was going to say as well, if you want to go go no further than Blue Marble Science, if you want a demonstration of gas pressure without a sealed container. Remember that one he did?
Yeah, that's the one I was going to bring up to watch.
Yeah.
I just thought you were going to get a kick out of that flat earther that I found.
That really was good.
That's priceless.
Yeah, I'm sorry I interrupted a bit. I'm sorry I preempted you. A little warning would have been good.
Well, we got there in the end. We got there. We got the laugh.
And he does have a couple of other videos to watch. So I'll play one. I'll play another one later. We'll stick to the subject for now, and then I'll play another one of his in a minute.
Cool.
I don't know if I've got a Big Blues one floating around.
On the subject of air pressure, when you go diving, I went diving a few times when I was younger. They put a big air tank on your back.
Oh, Mip.
Hey, Mip.
You, Mip?
Is that me or Mip?
I think it was Mip. Mip's having trouble with it.
Lots and lots of.
Oh, that sounds terrible.
Oh, yeah.
Yeah, Mip, you're really bad.
Try coming and that again, Mippet. Anyway, so those air pressure tanks, they put them in a sink just to make sure they don't explode.
Well, every time I go paintballing, what would you treat as say the buck, the stock of my marker is my air tank. Now we don't run at the pressure. That tank will take 4,500 psi, but where I play, their compressor only runs to 3,000 psi. So I've got an air tank next to my cheek that's got 3,000 psi of air pressure inside it, and it holds just over a litre of air.
Oh, so it's small enough you don't even have to have it inspected then?
No, they're good for 5 years, and then you get them recertified every 5 years because of the fact that it's holding 3,000 psi, potentially 4,500 psi. That's what mine rated at.
I thought under a litre or under 500. Can't remember what size cylinder you can. Some of the smaller cylinders, like the size that they use for the guns, don't need inspecting.
Well,
it might be half a litre.
Yeah, because I think most of the runs that we use now, you don't generally go below a litre because that means that you run out of air, and you try and match it so that you take out as much paint with you as your air tank will last.
Yeah.
Otherwise, you'll be able to take out 1,000 rounds of paint, but only have enough air to fire 500. And sometimes that you'll play a game, and then when they switch ends to play the game again, with the teams turned around, it's like, why aren't you playing? I ain't got any air. Well, I've run out of paint. So yeah, they generally tend to be at least a litre. I think mine are 1.1 litre tanks. But to be frank, you'd want it regularly tested anyway. If you're holding something next to your face that could hold air at 4,500 psi, you
Yeah,
want to
that's
know
300
that it's sound.
That's 300 bar.
Exactly. You want to know that it's not suddenly
I-
going to burst in your face.
That's the thing that I regularly use. I regularly use cylinders that run at 300 bar that don't require testing, and it is kind of like a bit concerning at times. You'd think, but
Yeah, 400 psi and flat earthers panic about 14.7 psi.
Yeah, and I've got 2 air tanks down in my kit bag now that are at 3,000 psi.
3,000 psi.
Yeah.
You know, this is the thing as well, because I don't know, you know, most of you remember, you know, the Falcon Heavy demonstration when Elon Musk launched the Tesla into space, right? Okay, the Tesla was hardly altered at all, right? But all the flat earthers are flapping and saying, "Oh, that's impossible! That's impossible! The tires would explode."
Really?
Yeah.
Yeah.
I mean,
you know, and it's kind of like, and it's hard to sort of explain to them. But hold on, there's the only differences between when it was on Earth and when it's in space is 14.7 psi. What makes you think there's like this huge, massive pressure building up inside the tires? You know what I mean?
Yeah.
You know, they might have even just let out just maybe sort of, I don't know, 15 psi or something, and it would have been fine. But they probably didn't need to anyway, because I'm sure the tires could probably take an extra 14.7 psi pressure.
I think
I'm pretty sure you can overinflate a tire by 1 bar.
Yeah, I'm probably sure you can, Alan. Yeah, absolutely.
I think the only things that they modified on that car were pretty much to stop it vibrating, because that's what you don't want. I think you'll find that suspension had probably been bolted up solid, and they might have added a couple of bits in there to stop everything rattling and moving about.
Exactly, during the launch especially. Yeah.
Hey,
Well,
Casual.
actually, there's a lot of weight reduction on that car.
Hey, Casual.
Yes.
You know, when that car's in space, imagine how much it's going to be worth when it returns, if it returns to Earth and on ground.
Yeah, it'd be good, wouldn't it?
Only car that's been in space.
It would be good if we could get it back down, wouldn't it? It'd be good.
And it'd be something that you wouldn't want to restore, because I can tell you now the paint would be faded as hell.
Oh yeah, it's orbiting the sun at the moment, and it's passed Mars a few times. Well, a few times, maybe once or twice.
But it'll have the same problem as the flags from all the old Apollo missions. You're pretty certain they'll be bleached completely white.
Oh yeah, of course.
Yeah.
There most definitely won't be much in the way of colour left on it.
No, not much.
All that UV and X, all that UV and X-ray and X radiation that it'll be getting.
I would like to have known how it affected all the plastic on the dash and all the rest of it. How that got affected as well. What that would look like.
Yeah, that'll probably not be. That'll probably not be good for that either. I would guess that there would be enough high energy photons out there to really screw it.
Somebody got a video? Press play.
Oh, bag of crisps.
Play.
Someone played a video before.
Sorry, I wasn't near the computer.
Yeah, they put a bag of crisps in some balloon and brought it down, and it hadn't changed its shape, but apparently they let out the air previously.
Well, that's the videos I'm looking for. I only found this one so far. I was actually looking for a balloon test.
Play this one anyway, Terry. Play.
Oh yes, that's a bit of a climb, Pikes Peak.
There you go.
I can just do a packet of them.
Yeah. Exactly what you'd expect.
But those chips are in a container.
I'll see if I can find.
What's happening there?
I'll play it again, but I'll see if I can find a better. This one doesn't show.
Slice Bar Kane did a good one with a bottle and a balloon.
Right, that's the one I've got to find then. Because we've got no information.
He just drove up the side of a mountain, didn't he?
Yeah, we've got no information regarding any telemetry like elevation, all that sort of stuff for that?
Oh, that's Pikes Peak. So that's about, if I remember right, that's about a 4,500 foot climb. At least the bit that they race up.
Yeah, and they have problems racing up it because whatever races up it has to keep adjusting itself to the changing in air pressure.
Yeah, exactly. You don't really need these calculations. I mean, it'd be nice to have. However, the proof is out there to say, look, this is what happens. Can you disprove it on your flat model? Of course they can't.
Well, actually, no. It's please explain how this happens on your flat model.
Oh, exactly. That's what I was trying to say.
Yeah,
you said it better than I did.
Oh.
And to which their first response would probably be, "Well, we don't have a model."
Exactly.
We know why you don't have a model because you can't model it.
Mm-mm.
Yeah.
And there's 3D software out there, and I've seen people use quite 3D software to do it. But even with that, they find it difficult to model their assumptions.
We know somebody on our side who had to invent the inverse cube law for light.
Yep.
And then he also had to introduce a toroidal something or other that actually we don't know about, but to make sunset work.
Is that the same as that planet Nibiru and the second moon that's invisible?
Oh no! This is shout out to Stingray and his model that doesn't work in the Antarctic. To which he replies, "But have you been there?" And I heard the plea going out yesterday in Jem's Discord servers that how come none of you flat earthers are trying to help Dean with his model? But we know the answer to that already.
Well, flat never tried to help anybody else apart from themselves, which is not surprising.
Which is why you see all the infighting that's going on again at the moment. Too busy stabbing each other in the back.
Whereas our side, which is the globe side, seem to be able to help, any creator, from Red to Fight to Flat Earth to even Seek Truth and Speak Truth that's come across. So yeah, why not?
Yes.
Yeah. I mean, the thing is that there are quite a lot of sensible people out there who can make a better effort at doing flat Earth than the flat earthers can.
Yeah.
Just because we know, that's because we know enough stuff to know what to allow for and what not to allow for.
Yeah.
But most flat earthers just become parrots. They should repeat and regurgitate what's been said to them by people like Eric and Nathan. And the other Nathan, and the other Nathan.
Mr. Sargent. Oh, yeah, all the Nathans. There's far too many of them.
Yeah, I now feel really sorry for my son-in-law.
What, Nathan?
Yeah.
Yeah.
Although of course, he does now get called Bob quite a lot. Sorry, Jim quite a lot now as well.
Jim.
Yeah. That's what he gets for being a Rosie.
Yeah, to the point that they have their Fiesta that they take to shows and stuff.
Yeah.
It's got the obligatory sun strip across the top of the windscreen.
What, Rosie and Jim?
It actually says Rosie and Jim on it. Yes.
But
actually, it says Jim and Rosie because it's got to be on the correct size.
Oh yeah. It's got to put the right way around, regardless of who owns it or drives it. It's got to be Rosie and Jim. That just makes it even better when he's sitting in. It says Rosie above him. It's got to be done. Oh bless. Well, at least they're owning it. If they're going to take the P out of you kind of got to go with it, haven't you? There's no point fighting it.
Rosie actually has a Rosie and Jim tat.
Oh, yeah. Why doesn't that surprise me?
Yeah, the whole thing and the duck.
Oh. Yeah, that's a bit after my time. All that stuff. I'm more of a the clangers and bagpuss generation.
Yeah, so same here. but you know, it was what I, you know, I did spend an awful lot of time when she was little watching Rosie and Jim with her.
Yeah,
And,
that's the downside of kids. You have to watch their crap with them.
And a TV series called Come Outside. There was another series she loved called Come Outside.
That rings a vague bell.
There was a dog called Pippin, and the woman who was in it, who was like a middle-aged, motherly, you know, sort of even grandmotherly woman, who flew a light aircraft that was painted in lots of spots. And they would go flying to places, which was kind of like just weird.
Oh yeah, shout out to Irish Stew. That's actually what I was thinking of when I saw Pikes Peak was Guy Martin taking his motorbike up there. That guy is a legend. Guy Martin. He's just.
I was a little disappointed when he that he managed to essentially put his Merlin engine through the workshop wall. Again, who tries to run a Merlin at 3,000 RPM inside?
Guy Martin. But you blame him? I mean, when they first shot that little program about it, and he's like, "Oh, I've got this Merlin engine." He's saying to the camera crew, "Do you want to see it? Do you want to see it?" You know, I'd be exactly the same. Look at this. Look, come on. I'll fire it up for you. You know, I mean, his excitement and enthusiasm is quite something.
Who else would start it up inside than Guy Martin?
I know. At least wheel the bugger outside first.
Yeah.
Remembering that in order to keep some load on the aircraft, it's got about half a propeller on it.
Yes. Yeah. And that's the same engine that they modified and put in quite a few tanks.
Yeah, that was
the Merlin became the Meteor engine.
Yeah, although if I remember correctly, the Meteor only did about 500 horsepower instead of the full 1,000 that the Merlin did.
The Meteor started out at about 600, I think.
Yeah, because I think it was the fact that they didn't supercharge it so much.
Yeah. Yeah. I don't think.
I don't even know if they
supercharger.
I don't even know if it had the supercharger on it.
I don't think it did.
Because like.
Let's have a look.
I can't find
Flat Earth balloon experiment.
Yeah, that's what I'm looking for.
You just scrolled it off the bottom of the screen, Terry.
Go down again.
Right hand side. Oh. Maybe not.
Yeah, so it's balloon experiment recommendations.
Oh, they did have to modify it quite
What's
a bit.
wrong with that?
Yeah, there's a big difference between a Meteor and a Merlin.
Well, they run in different directions. Huh. Automotive gearboxes ran the opposite way to an aircraft propeller, and changing direction required modification of the camshaft lobes. And they stripped off its supercharger reduction gear, etc., etc.
Does the direction change depending on which hemisphere you live in?
No. Oh, that's interesting. They actually started using the Merlin engine because they recovered some engines from crashed aircraft. And as the Wikipedia article states, whilst unsuitable for reuse in aircraft, the Rolls-Royce chassis division had begun collecting and refurbish them in hopes of finding a use. And then they were contacted by a chap from Leyland who sort of said, look, we're looking for engines to put in tanks. I think they put 2 and 2 together and got 4.
Yeah. Well, why wouldn't you?
Yeah.
Yeah, I mean, you know, they put them in MTBs as well. 3 of them.
Cromwell, Challenger, Avenger. Oh, that's a self-propelled artillery version of the Challenger. The Comet, the Centurion, the Charioteer, the poor old Tortoise that sits all on its lonesome down at Bovington, the Carnarvon, oh yeah, the Conqueror. Yeah, I bet that would be struggling in the Conqueror because they're bloody heavy.
Yeah. But yeah, they used to put 3 Rolls-Royce, they used to put 3 Merlins in the MTBs.
Yeah,
torpedo boats. Because my dad was a commercial motor mechanic. He'd been apprenticed, and he was just he was reserved. They made it. They hammered him with reserved occupation, so he couldn't join up because they wouldn't let him because he was occupation. And at one point he was actually working in Barking Docks with him on MTBs. With Merlins.
Interesting. There's a list of applications on the Wikipedia page, but they're all just aircraft.
We said they were Merlins. And I'm sure I've read somewhere else that the MTBs had Merlins.
MTB engines. Right, torpedo boat. Let's have a look.
As interesting as this, we're going off a bit off topic.
Yeah, I know. That's what I was trying to find this video to do with with these balloons.
Just trying, so we don't have any dead air, you know.
Yeah, Farmers and I were just chatting, so we don't have dead air.
Because that's the last thing you want.
It has some connection to do with pressure gradient, doesn't it? What you're talking about?
Well, I posted a link to a bottom.
Well, I guess yes. You've got a pressure you've got a pressure thing through the carburetor of the engine, haven't you?
Yeah.
How do you say it again? Disequilibrium. Sorry, I can't even say it now.
Relative disequilibrium.
That's the way you say it. Yes.
That's the
that's the
that's the Anthony. I think that was a travesty giving him that bloody award this year.
Yeah.
But it's so stupid. I just saw the video of his.
Sorry.
Yeah, it shouldn't have mattered how many votes he got. He should have just been second.
Yeah.
Because blah 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 blah.
Exactly.
I mean, just watch the video of his where he mentioned that the boats, because boats float on water, that they disprove gravity. I'm thinking, what is he trying to say there? Weird.
Displacement due to buoyancy. Buoyancy only works because of gravity.
Correct.
I'm trying to remember.
Right. The only reference I can find
to engines inside motor. This is from Crazations. Describe how a siphon works using density and buoyancy instead of gravity.
It's just pressure disequilibrium. Sorry. What was it using instead of gravity?
Describe how a siphon works using density and buoyancy instead of gravity.
Well, you can't use density and buoyancy instead of gravity because buoyancy is dependent on gravity.
Did he just say something right? My gosh.
Do you know, that's twice now that he's got something right. That video where he said that what's it? There's flat Earth has no sides or whatever. The one that Blue just did a video.
Are you talking to retard?
Are you going through your entire soundboard?
No, I just actually I could have even gone.
Of course.
Are you talking to retards again?
CC,
What a star.
remember his wife? He put out a video with his wife talking to him when he did the pumpkin. Oh dear, what a sad case. What a sad case indeed.
Yeah.
It's the only reason he does videos in his car, because he can't do videos from home.
Well, that's why most of them are doing videos in their car. I mean, you know, poor old CC has shown the entire world what we already suspected anyway. You know, why do you keep filming in the car? Because there's nobody there to stop you being such a bloody idiot.
Can I can I share something a minute? It's a good demonstration model of gas molecules on a planet.
Oh, please do.
What would happen if you what would happen if you remove the gravity?
Are you playing another clip from Riley the Retard?
No, it's not a video.
Because he did it. He demonstrated it himself, didn't he?
No, it's not a video. I'll show you. Hold on. All right, can you see that? Okay.
Yep.
Right. This is a well, I'm sure some of you probably have seen it, but this is more for the benefit of the peanut gallery.
Didn't Riley didn't Riley do this?
Yes, he did. He did.
He turned gravity off.
Oh, they? Oh, all right.
Which is
okay.
what you're about to do.
Yeah. Thanks for.
Yeah, don't turn gravity off. We'll all die. We'll die. We'll die.
So the benefit of the peanut gallery then, right? This is this. I don't know if you can see my cursor, but on the right hand side you see the panel where it says Planet G. I've got my cursor on it. And
yeah. You can just see it.
So at the moment it's 5,000. Yeah. So we turn the gravity to 0.
No, we're gonna die.
Now all those little white dots are the molecules of air, aren't they? That's basically Earth's atmosphere.
Yeah, exactly. That's what I'm saying.
Off, yeah.
There we go.
Riley did a video.
There goes our gravity. There goes our
And he was
atmosphere.
basically saying how gravity isn't responsible for holding our atmosphere down. And he did what you just did, and he turned gravity off.
Yeah, I don't know
and
why.
The atmosphere flies away.
I don't know why he did that.
Yeah, because he debunked himself in his own video. And it's not the first time he's done that, but it's a very graphic way of debunking yourself when you're saying gravity is not responsible for holding our atmosphere down. Here, let me show you what happens when you turn gravity off.
He debunks himself by showing it. Idiot.
But when you tried to tackle him down on what he said, oh no, I didn't mean that. Yeah.
No, that's not what he meant.
Yeah, but that's what.
That's not what I meant.
But that's what he said.
No, but that's not what I mean.
Going out to
Just
space.
because I say that doesn't mean that's what I mean.
Yeah, exactly. Well, what a
then I'll go on a narrative to explain what I meant, but not what I said.
It's like that the $1 million guy who did the recent challenge. You know, he's moved the goalposts yet again.
He didn't, did he?
Well, he tried to debunk Simon Dan's point of view.
I've just turned gravity back on again. Look.
Oh, thank God for that.
Oh, thank you.
There you go.
I'm finding it hard to breathe.
How much of that atmosphere has actually escaped?
Yeah, but not all of it's going to come back.
No, it won't. No, because unless I turn gravity way up, which case it might get.
No, don't do that. I'll weigh more than what I am now.
Yeah, you weigh twice as much as you do now because I've just got twice the amount of gravity. No! You're about 2G there. Yeah, there you go.
I'll have to put some more air in the tyres.
No, I just thought it was a good demonstration. Like I said, I'm sure some of you seen it, but not everybody in the chat.
No, it is a good demo. Yeah. That's quite a good little model.
Another one to mess about with is that game. Oh, blimey, it's not really a game. I wouldn't call it a game. Where you can mess about with soda, like universes.
That one.
And
yeah, I've heard of that one.
Yeah.
Universe Sandbox?
Yeah, Universe Sandbox.
That's the one.
Yeah,
yeah. That's a great one. If you mess about with gravity and temperatures and all sorts of things, you can see what happens to the Earth or any planet, or what happens to the sun if you lower the temperature or raise the temperature and stuff like that. It's good fun.
But it's amazing that you got this software out there that show you not only Google Earth to show you the Earth, or the Google Maps to show you where you live, which is what people mostly use. And you got 3D software out there to do 3D architecture and 3D buildings and 3D Earth. Yet have not yet to see any software that can prove the flat Earth.
Oh, and strangely, the temperature of this fake planet is going up because I put it at all gravity because there's more air pressure. Interesting.
Yeah, I did. Somewhere on this PC, I did draw in AutoCAD. I drew a circle, 1-to-1 to represent the size of the Earth, and then on the very top, I drew a 1 meter long spirit level because I wanted to see what the distance would be at sort of one end of the spirit level between that and the Earth. Something in picometers, I think it was.
Farmers, it's about 78 nanometers, which is far end of the. It's actually equivalent to a wavelength in the far end of UV, because UV is 200 nanometers to about 35 nanometers. So it's a way. The only way you would see the gap is if you were looking with X-rays, really, because you need to be looking with at the gap with something that's got a wavelength that's smaller than the gap.
Right, I've just found the drawing, and I'm now trying to zoom in enough that I can actually measure the gap. Oh God, this is going to be difficult. Hang on a minute.
I've actually done the calculation, and I didn't use 8 inches per mile squared either. I actually did it using the correct form.
Has anyone found the balloon going up in elevation stuff yet? Because I'm still having trouble finding them. I know they're out there. Just don't know who else has done one.
Irish Stu, Oakley would actually be correct in that statement. If people wanted to lose weight, they should go to the moon.
Yes, you'll lose weight, but you won't lose mass.
But what most people want to actually do is lose mass, not weight.
Yes. Oh, here we go. I just had to reset the units in my CAD program. It's 0.00006485 millimeters. That's how much of a gap there is between one end of the spirit level and the Earth if it was a perfect sphere.
Yeah, I guess I think the difference between what you've said and what I've said is down to what value you use for R.
Yes.
R value.
Now I'm going to have to set the units back because I don't work to
because
there's precision.
Because there's all sorts of different. There's many different values for. I mean, I believe the stated mean value for R, if I'm remembering correctly, is 6371009 meters.
Oh, Aaron in Armstrong in the peanut gallery. I was looking for videos that I've seen of people putting a balloon in their car and going up in elevation, and it should have the recorded elevations of where they were at and how high they went up in elevation, and the balloon is affected by elevation change, which is your pressure gradient. That's what I'm looking for.
So my spirit level, according to Aaron's, got to be 31 miles long, which is 49,889.664 meters.
Because we're looking for proofs for
Okie
pressure
dokie.
gradient.
Let's try and draw that. So I will have a line that is 49,889.664.
I would disagree with your number of meters, but only because I tend to use a higher level of accuracy than most people.
Well, I just use a little conversion on my phone.
I've got people at the peanut gallery helping me, but no one on the panel helping.
Yeah, and
Yeah. And
I am looking at the moment, Terry.
Okay, thanks, Casual.
you need a new secretary. You need a new secretary.
I was gonna get Andrea, but she's not around at the moment.
No, it doesn't seem to be.
I'm only doing this because I happen to have CAD open because I happen to be working in CAD at the moment.
Yeah.
I've lost my spirit level. It's only 31 miles long. Oh, there it is.
How could you lose it?
Well, when you zoom extents, so you can see the entire planet. Because the great thing about AutoCAD is when you draw something in model space, you draw it at 1-to-1. So if I draw a circle that is a diameter of 40075000000 millimeters, that's how big it actually is. So that if I I know you're joking, Aaron. If I draw something full size, if I draw something in AutoCAD, I actually draw it full size. So the apartments that I'm drawing at the moment are.
Do you draw it in millimeters or centimeters or meters?
Millimeters. Right. The apartment I'm drawing at the moment is 13,708.6 millimeters across. 13.7 meters.
So if you want to draw a circle that is the diameter, the average diameter of the Earth, you need it to be 1.274 times 10 to the 10 millimeters.
Yes. Yes, that's. But I don't generally have to draw anything that big in AutoCAD.
Yeah, but that's the size of the circle you have to. That's the diameter of the circle you have to draw if you want it to be the average diameter of the Earth.
Yes. Yeah. The great thing about AutoCAD is you do all your drawing work in what's called model space, and everything is 1-to-1. So, like these flats, they have the thin plastic ductwork stuck to the underside of the slab, and that's 204 mil wide by 60 mil deep. So when I draw two lines 204 mil apart, that is a 1-to-1 representation of how wide the ductwork is. When you then go into what's called paper space, you then set the scale of the drawing, which in this case is 1:50, and that will fit on an AO sheet. But in when you do all your drawing in model space, the model, I said the M word, the model you're creating is all at full scale.
It's all done. It's all done to full scale.
Yeah. And as we're over in Europe, not in Freedom Land, we work in SI units.
Yeah, to be honest, that makes perfect sense, because if you're creating drawings in a CAD program, you really want them to be. Sorry, if you're creating things in a CAD program, you really want them to be created life size, don't you?
Yes. Yes.
Because then you can interface them with other things that have been created that are life size.
Correct.
And then
I'll see you guys later.
Ooh. Terry.
Yeah.
I think I'm going to have to go because I'm starting to get some neck pains that are related to what I said to you earlier on about when we were stressing over OBS.
Yeah, well, I'm sorry about that, Alan. I didn't mean to stress you out.
That's okay. It's just like, when you keep trying stuff and it doesn't work, it's a bit like banging your head against something, isn't it? So,
well, maybe I've got more patience than I should have sometimes.
Yeah, it's all right. I'm just say.
Well, thanks for your help anyway. I'm glad you're able to sort it out.
I think the Pauls is trying to have a bit of a go at the minute. So, yeah.
I'll catch you tomorrow sometime then.
Hopefully, yes,
right,
mate.
take it easy.
Okay then.
I sure. Yeah, I better go before I
Okay.
get really bad.
Okay.
See you all later, guys.
Later,
Yeah,
Alan.
see you later.
Bye. Bye. Peter's put something in the side chat, in the internal chat here.
Oh, did he? Before he left,
he
or is he
found it.
still? I thought he had to leave.
No, Peter. I'm talking about Peter's still here, not Alan.
Oh, I said Peter. Yeah, that was his pressure thing that I showed before.
He says he's just hiding.
He's just hiding.
Yeah,
I
he
just
probably
put
doesn't
your
want to talk. He's
pressure
got a
thing.
headache,
Did
probably.
you do it again?
No, he's just put something in chat there now. I don't know what it is. I haven't looked at it yet.
Yeah, that's his pressure thing with his watch.
I don't know. I haven't.
Yeah,
I haven't looked at it.
You already played that.
Yeah, I have no idea.
I already watched that, Peter. But what I'd found is this. Professor Phil says, have you seen this video of mine? It's more or less relevant. Okay, Phil. I'll grab that. Before I forget. Open link in new chat tab. Alright, I've got it now. Okay. Share this. I don't know if there's any sound, but I don't think you need sound. So obviously he's...
No, I think it's...
It says here, I sealed a balloon in a bottle at 1295 feet above sea level. So is it sea level?
And then opened it at
14,000 Pikes Peak. So anyone want to guess what's going to happen? I know what's going to happen.
I think most of us do.
Yep.
That's a very good demonstration, actually.
We've got to act dumb. We don't know.
There you go. It's got the lid on it. There's a seal container.
Oh, how did the balloon get bigger?
Oh my word! I wasn't expecting that.
Magic. That was magic. We've got to see that again. That's definitely magic.
It's mathematical. Why can't I find slides of it?
There you go.
Oh wow, that's amazing.
I wonder how flat earthers can explain that. I wonder.
Yeah, I'd like to see him try to.
Yeah.
Okay. There is one where somebody's driving up a mountain with the balloon over a bottle. That's the one I was looking for.
You know, Riley won't accept that, won't you?
No.
That demonstration, because he didn't use the scientific method.
Yeah.
That's what Riley would say. It's not an experiment. Well, it's not an experiment anyway. It's a demonstration. Doesn't have to be an experiment.
Professor Phil's
it's an observation, and observations are not part of the scientific method.
Yeah, exactly.
According to him.
Yeah.
Phil says this is more or less relevant. His video.
Right.
It's more or less relevant. How long does it go for?
What, relevant-ish?
I don't know. Okay.
Could a demonstration or observation be classed as evidence? It can't it? Surely.
Well, I think the explanation has to have the citation of the evidence in the explanation.
Yeah, but that demonstration of that guy, with the balloon inside the bottle, opening the bottle at a higher altitude, it expands.
Yeah.
Right. So, that could be, surely that could be classed as evidence.
But he hasn't got no relevant
gas pressure
evidence to show his elevation. He'd had to have filmed that. He'd had to have filmed it at the lower elevation to show what elevation and show what proof of elevation he was at when he sealed it. And then the
So
video.
if he did that,
So and then drove up the mountain without breaking the camera feed, showing your elevation change, and then get to the top with your elevation, and then opening it up, all in one take.
Yeah. I get that, but then again, you could say, well, that's not really classed as an experiment, because according to Riley, I'm putting myself in Riley's mind here, right?
Ooh.
So according to Riley, he might, but he would say, oh, well, that's not a scientific method because that's not a science experiment because you haven't followed the scientific method.
Oh, okay.
But
so
then
we
again,
need
you
an
could say,
independent variable.
But then, hold on. But then you could say, well, it's still evidence, isn't it? And I'm thinking, well, is it evidence though? Could you class that as evidence of a gas pressure, a lower gas pressure elevation?
It's an observation, and it's perfectly fine, because as we all know, they keep asking for empirical evidence, and empirical evidence is founded on observation.
Yeah.
That's what makes it empirical, because you've observed it.
Yeah.
And that's where the whole argument, well, one of the reasons why the whole argument falls down. That
Yeah, I thought Slide did it, Demon Orb, but I can't find the video.
No, I can't find it. And I know for damn certain he did.
Well, I've got two people out there that are doing it casually. You were looking for it.
I just had a quick look through his channel as well. I can't find it.
No, I can't either.
Oh.
Unless it wouldn't have been deleted, would it?
Not that I can think. It's just probably hidden in one of his videos. We just don't know which one it is.
It's most definitely it's most definitely Sly, because it was in his BMW.
Yeah, no, I couldn't see it. I looked. See it.
Whichever German mountain it was he was driving up.
I know the one you're talking about. I remember seeing it myself as well. Yeah. So you know exactly the one you're talking about.
Yes, that's right, Phil. We know observations are still evidence.
Yeah.
Well, we'll watch Phil's video and we'll do a bit more Googling. I can't do Googling while I'm watching the video, so I'll let you guys do the Googling.
No, I want to watch this.
Oh.
Right. You watch it. I'm going to go learn something.
Somebody's got to Google. Somebody's got to.
Somebody's going to put my kettle on, because I haven't been able to train the cats to do it.
Peter's said in the side chat he's still looking. So in the internet.
Yeah. Okay.
I think it's gone, because I just had a quick scroll through all his videos and I couldn't see it.
Okay. We'll see what Phil's got to say.
It a strange title.
And I'm sorry. This is probably. And I'm sorry. This is probably pre-mic upgrade, so I might have to turn the volume up a little bit.
Okay, folks. So
yeah, I'll tweak the volume a little bit.
Today is have a look at these two hypotheses, and that is whether or not the Earth is flat, or whether or not the Earth is a sphere. And
let me know out in the peanut gallery if that's loud enough for you in YouTube.
Now, we've got alternative hypothesis that says that the Earth is flat, and if we look at the evidence and then we accept that, we therefore will be rejecting the hypothesis that the Earth is a sphere. Alternatively, if we find from the evidence that our conclusion that the Earth is a sphere, we will reject the alternative hypothesis and accept the null hypothesis. So let's start with the alternative hypothesis. So there's two possibilities. I'm looking at two models. Let's have a look over here. Okay, we've got two models going. Over here, the possibility that there's a flat Earth and above that an atmosphere. The problem is that this is not contained, and as a result, because our observations show that there's a gradient up here, this we would have to contend with what happens on the sides over here, and how would the sun affect the atmosphere that's over there. So I would reject this one outright, because it's nowhere near conforms to the observation, and it also spoils the notion from the flat Earth model that space even exists. That's number one. It would have to exist in this case, and also you would need a force to hold down the atmosphere. Okay, so let's cross that one off. That one is other than the flatness of it, is pretty much close to this hypothesis over here. So let's look at this one here, which is common and accepted throughout the Flat Earth community. Now, there's quite a few people in the Flat Earth community who purport not to have a model, which is equally absurd. So to say that you don't have a model, however, this one is not right, it doesn't work, even though it meets the observations, is nonsensical. Okay, so let's have a look at this. Here we have a dome surrounding, we don't know what that dome is. The Flat Earth people will tell you that nobody knows what it is, and there's many different conjectures about what it might be. The idea that it might be some sort of crystal or some sort of glass, or I've even heard that it's some sort of liquid gas, and that came from a very, very tall gentleman in Thailand. Okay,
we know who that is.
In this particular situation, just according to Dalton's law and gas laws in general, in this case, with the sun rotating and giving off energy, the surface of the sun is hot, so around 6,000, giving off energy all the time and going around here would cause the gas in this, underneath this dome, to become homogeneous. In fact, this gas would continue to heat up and become homogeneous. Right? Now, the other issue is has a fixed volume, so that would also increase the pressure underneath this dome. So there would have to be some mechanism for allowing that pressure to dissipate. Nothing of that is even proposed. Okay. So the fact that this would have a fixed dome has problems associated like this. Okay, let's have a look at what the evidence would be expected from this. Okay, so if this was a fixed dome, first of all, you'd expect, this is what you'd expect, increasingly hot gas and temperatures as a function of time. So the longer that time went on, and remember, if we believe the creation story, there's 6,000 years in here. So at 6,000 years, this sun has managed to go around here underneath this dome, and that would have, in that time, caused a massive increase in temperature. We can actually do the maths on that and work out exactly what, how many calories of energy would have dissipated by then, and how much this gas would have raised. But suffice to say, it would be a significant temperature increase for all the gas under this. Okay. There would be no pressure gradient in here. Okay, all the gas would be homogeneous. If there's any convection currents, there would be convection that you normally expect, where things heat up, rise, come back, just like you'd see convection currents that happen in a pot of water, for instance, on the stove. So that would be a rotating convection current around there, but pretty much the gas there, gas molecules would be homogeneous and certainly be roughly the same temperature. Okay, the fixed volume is a real problem here, okay, because it's going to have an increased pressure. So as the temperature increases, the pressure will increase as well. We know that from Boyle's equation. And so if we fix the volume, temperature and pressure are proportional to each other. Now, so again, this has had enough time. 6,000 years with the sun above there creating this additional temperature in a fixed volume would have created a significant amount of pressure. And certainly there would be no gradient pressure. This pressure would be homogeneous through the entire system. Okay, so again, increase in temperature with altitude. So again, you'd expect, if indeed we did have this convection currents running through here, which I think we would, then we would have an increase in temperature as you went up, because the closer you got to this source of energy, the sun, the hotter things would get for you. Okay, that would be undeniable. Okay, altimeters would not work. So because of this homogeneous pressure in there, then you know, altimeters are basically barometers and work off pressure. And because they don't have that, this would be homogeneous. Therefore, the altimeters wouldn't work. Okay, so the conclusion here is this does not comport with actual observations. So these evidences that are expected do not comport with the actual observations. Okay. All right, let's look at the other one and then and see what we can get from that. So over here we have the globe model, which is the null hypothesis. Okay, in this particular model, there is a pressure gradient close to the surface, as you can see depicted here. The gas is much thicker, more molecules, if you like, per cubic meter as you are closer to the Earth, and then as you move away, it gets less and less, and you see depicted up here practically very, very few molecules compared to what they are down here, and compared to the size of the space that's been occupied. Okay, so if we have a look at that, we can see here a great pressure gradient, high concentration of molecules close to the surface, low concentration of molecules. So I'll make that up. So low concentration.
If we had Phil in here, he could answer Charlie in the side chat. As gas clearly has weight and even mass, if there is a dome, there would be an atmospheric pressure gradient.
You kind of would think so, wouldn't you? But I don't know. Perhaps Professor Phil should come in. Why don't you come in, Professor Phil, if you're still there?
Yeah, if he's still out there, Phil, are you able to come in?
Of molecules much further away, and this arrangement just keeps going indefinitely. So because of that, there is no requirement for a barrier between the two. So what the molecules that are close to the surface are being held there by gravity, and one would say, well, do we get some of the atmosphere leaking off? Yes, that does happen. Okay, but by and large, the energy that's required to make it leak off is less than the force that gravity is acting on it.
He's coming.
And,
yeah.
So some people will say, well, gravity is not a force. When gravity is applied to a mass, and gas has a mass, drop a kilogram of carbon dioxide on your foot, and then come back and tell me that it doesn't have mass, I'm afraid you'll find that it does. So gases do have mass. Force will act, gravity will act in concert with mass to create this force, and it's this force that keeps the molecules on the planet. So basically describing that in this equation, that force is equal to the mass times the gravitational acceleration. Okay, now what evidence would we expect to see because of this? We would expect to see that as you get up higher and higher in altitude, you'd have less and less gas, so you'd find it struggle to breathe if you were, say, at the top of the mountain. Now, does that comport with the observation? It certainly does. If you climb a high mountain like Everest, you'll definitely have to take breathing apparatus with you. Okay, people die up there because they don't have sufficient air to breathe. Okay, so pressure decrease with altitude. So as you go higher and higher in altitude, the pressure gets less and less, and this is expected because the molecules get less and less. So there's fewer and fewer molecules bashing into each other, fewer and fewer molecules creating mass. The pressure will definitely increase as you go up, and it does. This is a measured fact. Okay, the pressure decreases as you rise. Okay, so as you go from the bottom of the mountain to the top of the mountain, not only does it make it impossible to breathe because there's not enough gas, but the pressure also decreases. We know the pressure decreases too because if you wanted to boil water, for instance, at the surface of the earth, you'd have to boil water. It would be boiling at around about 100 degrees C, 200 and 373 degrees Kelvin.
Hello.
And then,
hello, me.
And then as you go up towards the top of Mount Everest, it would boil at 70 degrees C. Okay, so it's considerably less.
Yeah, we'll just watch your video and then we'll
because
talk.
it's boiling at much less temperature, that proves that the pressure is much less. Okay. Temperature will decrease with altitude.
Can you hear me?
That
yes.
comports with
yes, we
observations
hear you.
as well. And
okay.
It's a
all right. So you wanted to
because there are less molecules up there.
I was going to watch the video first.
I'll stop it. Yeah, then I'll explain to you. So Charlie has asked, would there be a pressure gradient under a dome, and provided there wasn't a sun heating the whole thing up, yes, the gravity would cause a pressure gradient underneath a dome. So that would happen. But that is negated by the fact that there'll be a sun. So imagine like a pot of hot water. You know, you're going to get convection currents, and eventually the entire gas will become homogeneous. Dalton's law proves that. And as you heat up the gas with it, the gas has no way to cool down. So it's just going to continue to get hotter and hotter and hotter underneath this dome. So the whole thing is preposterous.
Yeah.
Does that explain it for Charlie?
I don't know.
Yeah, sure it does. Well, it makes sense to me.
It has to, because that's all.
You might as well get
the sun underneath the dome is what would stuff up the pressure gradient. Because as you go further and further, closer and closer to this sun that's underneath the dome, it's going to get hotter and hotter, not cooler and cooler. In a pressure gradient, you'd expect it to get colder and colder because there's less and less molecules and less energy. Well, this is not the case if there's a sun in the middle of the thing. You can see how that would completely stuff up that model, this pressure gradient model, because it must get colder and colder if there's a pressure gradient, unless the gradient's upside down, which it can't be because we can breathe.
Yeah.
And we know heat rises, so
yes, and heat's going to rise. So, and because the heat rises, you can imagine it just common sense will tell you that you'll get convection. In other words, the heat will rise, it'll come down again, it'll be replaced by and continues in a circle until it becomes homogeneous.
We wouldn't have a North Pole. With the ice, it'd be melted.
There would be no ice around Antarctica, that's for sure. So the whole thing is just so ridiculous. It's how can at least a half-baked flat earther not see that?
I don't think it's a case of them seeing it. It's a case of they don't want to see it.
Yeah.
Yeah, it
a
has
lot of them do understand that. They just won't accept it, or they won't admit it, or both.
Yeah.
You know, it's just.
Now Charlie says, "Sorry, no. There's still a gradient. It's a basic aspect of the barometric formula."
Yeah, that would be true if there was no sun, Charlie. That would be entirely true if there was no sun. But the sun would completely stuff that idea up.
Yeah, because they've got the sun. What Phil's demonstrating here is the sun inside the dome. So you got something that's actually heating everything.
Yes, exactly. So it's
yeah.
like a convection oven.
No, we're not saying you're a flat earther, Charlie. No one's
we're
accused you of a flat earther.
No,
it's
we know where you're coming from.
Yeah, you're just asking. You're just making statements to clarify things. You know, that's how I tend.
I know it's hard to wrap your head around it, but it's because the dome that throws the spanner in the works, because it makes it a sealed environment, and that's what confuses people in that way.
I've dropped a link on the internal chat, Terry, that might help.
Yeah, but definitely, if there was no sun, Charlie would be 100% correct. There would be a gradient.
I've got something to say. The dome, though, it's a it can support heat transfer. It's a good thermal conductor, and that's the sun's heat radiating outwards. The sun's heat radiating outwards, and it being a thermal conductor and being colder at the edges where the sun isn't also creates the weather patterns. I'd like to add that.
Very interesting. Okay.
You
need to demonstrate that in physics, but yes, that's a reasonable hypothesis.
Thank you.
So the dome is made out of something that will dissipate the heat from the sun.
Speculatively, yes.
Yes. Okay. Well, we'd have to have. I still contend that you'd get a convection current anyway. And the other thing I would contend is that the higher up you go, the hotter it would get because your dome would be continuously hot as it tries to dissipate the heat. So
and
therefore, it would never get colder as you got up. It would get hotter.
So in theory, you wouldn't really get clouds, because clouds could only form where the pressure gradient allows it to form.
Yeah, but the clouds are the dome is conservative estimates put it at maybe 8,000 kilometers high. So the clouds sit well below that. So it doesn't matter. And if there is heat accumulating up there, you could call that the thermosphere underneath the dome. There's not a lot of density of atmosphere up there to conduct the heat. So yeah, it all works. It's fine.
Hang on.
So with that
Earth's atmosphere.
With that though, Stingray, I'll just we'll do a little bit of a mind experiment, because I know that everyone in here is capable of doing that. If I half fill a jar full of water that's coloured red, and then get hot water that's in a container that happens to have a nice long straw that I can put at the bottom of that room temperature water or cold water, and this hot water happens to be blue. Notice that I did everything back to front just to confuse everyone. And then poured that hot water at the bottom of all of that cold water. These two different temperatures would not necessarily mix. The hot water would actually go to the top.
Of course.
And it's called a flaming margarita, and I'm up for it. Just
the same thing would happen to the air within the dome, though. Is my point.
However, the difference there is on one we've got a semi-uniform density, on the other we've got a gradient. So that is actually what happens, but there isn't enough conductivity of the density of materials the further up we get. So it affects.
So then, on your premise that you're saying a hot air balloon would not work.
Yeah. This is thousands of kilometers high. There's no. You would be able to go up to the point where it seems very. It seems very cold, and there's not a lot of atmosphere, and the hot air balloon has no lift or we'll call it relative density disequilibrium, vectored force upwards. So it would lose that vectored force because there's not enough media now. There's not enough differential disequilibrium to push it up, and that's still nowhere near the top of the dome. We're thousands of kilometers above that, so
Yeah,
it
but
still works.
as that air got closer to the sun, would it not have transfer of energy to those molecules and then continue to go up further, quicker, because it's getting hotter and hotter as it gets closer to the heat of the sun?
I agree with that.
Except the issue there is the density of the medium that it would be in. It would run out of that density to be able to do that.
Jesus, you're the master of
bullshit.
Yeah.
He's a master of playing the devil's advocate. Is
You
what he
have
is.
really you have played with them for too long. You're too good at this.
He's made a couple of good points. Okay, he's made so I'm willing to entertain his hypothesis.
No, that's good playing out devil's advocate, and you need to sometimes, I think.
Well, no, because I mean you can just add magic to your dome as well, and you can really make it sing and dance then. So let's just
Can I watch the rest of this and then we can get on?
Yeah, go ahead. Yeah, please.
Then we can get on with the next video after that.
Molecules. Expressing the energy that's up there. So for that reason, the temperature decreases. So temperature relies on the fact that there are things to heat up, such as some sort of mass to heat up, and because there isn't enough of them around, therefore there isn't enough energy, and therefore it gets colder and colder the higher up you go. People will say, well, what happens in the thermosphere? Okay, well, again, the amount of temperature, there isn't a blanket amount of temperature around. You can't say, well, I'll go from here to there and then all of a sudden it's going to be hot. It's nothing like that. Hot relates to particular items that are in that vicinity. Okay, everything else around it is cold, and I mean really cold. So approaching absolute zero. So we talk approaching 0K, right, which is minus 273 C. So things that are approaching that temperature, absolute zero, in areas where there is no energy or very little energy. So when items are there and they're exposed to the high energy, then they become hot, sure. Okay, what else have we got here? We got low concentration of gases, okay, at high altitude. So I think we've gone over that. So again, this low concentration at high altitude, well, aeroplanes can't fly beyond a certain altitude because there just isn't enough air for them to be able to fly through. Aeroplanes need to be able to have an amount of air that passes over the top of the wing and a number of air that passes below the wing, creating this pressure difference which gives the airplane lift. So it's got two issues, the airplane, with that. Number one, it doesn't carry around it sufficient of its own oxygen like a rocket does to be able to not need oxygen from the air that's around it. So if it's too high, there's not enough of it to sustain combustion, and again, if it's too high, there's not enough of it to maintain lift, so the aerofoils don't work. Okay, now in a nutshell, again, this is quite brief. We could probably take both models to much greater extremes, but this is going to be a short video. So again, all of these evidences comport with the observation, all of them. Okay, so now let's draw some conclusions from the evidence that we have on this board here. So based on that, does not comport with observations, that these evidences that would have to be available if this model was right. These things here, no gradient, for instance. Okay, if we had this dome, all of those things would have to be true, and that does not comport with actual observations. Over here, in this case, all of the evidence, all of those that we've been through there, comport with actual observations. So we can only reach one conclusion. In this case, we have to reject H1, the alternative hypothesis, and we will accept the null hypothesis. The Earth is in fact a sphere. Thank you.
Who's got the radio on?
Yeah, I heard that. Terry, Boggs has said that he's found Sly's video and he's posted it in Discord apparently somewhere.
Yeah, it's called Flat Earth Ranty Under Pressure. Do we need to address anyone else before we do this? Charlie still seems to be.
Terry, did you hear what I said?
Yeah, I've got it.
Okay.
I've got it.
Okay. Yeah.
Terry,
okay, I wasn't sure whether you heard me.
I dropped another one, and I'm just about to drop another one for you, Terry.
Will you stop dropping them?
I can't help it. It's all right. Just spray the spray. It fixes it.
I'm glad I can't smell.
Yeah, so that second one that I've dropped's really good as well.
Okay, I got Flat Earth Ranty Under Pressure. That's the Sly one with the balloon. The one you dropped's called Classroom Friendly Air Pressure Demo. I just did Professor Phil. I better put that in homework. That way I've got it.
And there's one other that I dropped in there as well.
I'll put it in homework. That way I can put it up later. Editing. That'll go under the. I'll put that under the description. Right, that's that done. Out of the road. Okay, Charlie. Again, I think you might be considering the dome as producing an excellent isolation with the rest of the sky is cold. I understand it, Charlie. I don't know what the problem is. Oh. Minimize that. Don't need that in there. I've only just got YouTube running through OBS, sort of, so I'll tidy it up for next time when we're here. But at least I got it all fixed. That's the main thing. Silly me for pressing buttons that I shouldn't press. Pressing settings.
What you show them, it's still, they're going to find some. Greetings and salutations, everybody. I thought I'd do a response. This is not exactly in the way that the. Hey, oops, I'm echoing. Where is it? Scroll up. There we go. So, sorry about that. I had the Hangout playing in the background there, and I was hearing myself. Obviously, what I'm about to show you is, well, for most of you, it's not new, and it also does not meet the impossible criteria as laid out by Ranty. Okay. Now, notice I'm saying impossible criteria. Okay. Basically, what he wants you to do. He put out this little video, and I put a comment below it. You won't see it because Ranty has me blocked. The reason why people like Ranty have me blocked, and Ranty actually said it in Flat Earth Debate 619 live. Somebody told me that I need to go over there and listen to that because they were talking about, they had the dude on there, what was his name, Flat Hero or some shit, who was explaining why he wasn't going to pay Wolfie out and all this, claiming that he meant paper charts, but in his bet he never said paper charts. But nevertheless, and the dude was about to give in to that, you know, as far as saying that, you know, he didn't specify. But Ranty actually says in that video, all by himself, he says, don't give anything to Globers, never concede to anything that a Glober has to say. Now, that in itself means that no matter what you show Ranty, even though Ranty has taken more photos in support of the globe than I think almost any other flat earther, Ranty he's ranty. He's a flat earther, and like most flat earthers, if not the majority of flat earthers, it does not matter what you show them. It's still they're going to find some excuse for it, all the way up to the new and most recent atmospheric dome from Jeranism. But I lose you. But this is the thing. Ranty put out this little video here, and he's pumping up the tire on his car. And he's saying that pressure cannot exist without being in a container. Now, I'm going to say one thing because, I'm actually an honest person who can concede to something. The point that he's trying to make here is that inside of this tire is obviously going to be a higher pressure than the air pressure outside. That part is obvious. Okay, that's why it has to be in a container. However, he's using that as the analog for the atmosphere not apparently being sucked off into the vacuum of space. And now, and he even alludes down here to some kind of money being involved here. So whatever. But you see, Ranty, have you never driven over a hill before? Okay, because while I will admit that when you put 28 pounds of pressure in here, if that's what it was, PSI, there's a symbol up on the machine that says 28. If you are putting that much pressure into here and all this, because the pressure here and here is different, then of course you're going to need to do that. Now you're going to use that as your analog to say the atmosphere is a higher pressure than a vacuum. Okay. But what you won't find inside of this tire is a pressure difference from ground level to the top of the tire. Okay, I would like to see you demonstrate that because both you and Riley and I guess by default also Nathan have denied that very point or have deflected it. Okay, I heard Riley come up with some kind of gradient table and stuff like that. These are gradients that depend on gravity. Okay, so you can put it whatever way you want, but you cannot demonstrate it without gravity. Now, yes, if you put 28 pounds of pressure in here, it is going to be higher pressure because it's in a container. You put a hole in here, and the high pressure is going to escape to the low pressure. Same thing with a swimming pool. Okay, however, a swimming pool is not in a fully round container, but if you go down to the bottom of the swimming pool and your ears start pressing in, your eyes want to come out of your skull, okay, because you're like at 4 meters deep, 5 meters deep, okay, that's also pressure. And now the funny part about that is that pressure, because the air above it, the air above the water is actually at a lower pressure than any of that water is. High pressure moves towards a low pressure, so therefore that water should actually be shooting out of the pool. Now, if that sounds absurd to you, it's because that doesn't happen. The reason why that doesn't happen is because a force, in this case, the force of gravity, is pushing down on the water. And as you go deeper down in it, there's more water sitting on top of the water that you're currently at that level. And therefore you have pressure, a pressure gradient that goes down and increases as you go down deeper in the water. It's pretty simple. You can actually demonstrate this, that pressure. I mean, if you want to deny that it exists, which I really hope you don't deny that exists. You can actually demonstrate this by getting a cylinder, and a relatively tall cylinder, one that you could fill up with water, and then put a hole towards the top, a hole in the middle, and a hole at the bottom, and then open all three of those holes at the same time. The water at the bottom will shoot out farther, the water in the middle will shoot out a little bit less, and the water up top will shoot out a lot less. Okay, that's a pressure gradient. Okay, this very same pressure gradient we actually experience in nature. Now, I did this not too long ago. I am at about 400 meters above sea level. I realize that I am not at 14.7, something like that, PSI. I realize I'm not there. And But this was the point that I had to make. The point is, I put a container, okay, because this is to measure how much air is trying to expand. Okay, the air in here is currently at the air pressure that I am at where I'm parked right here. And I put a balloon on top of it, okay, to cover the top. But since the balloon is flexible, the balloon will show how much air is actually trying to escape because of the change in the pressure gradient as I drive up this hill. Now I drive up 400 meters, okay, and that's just what that is, man. So I'm going to let that play in the background here. Like I said, this was just me. All I did, the only reason why I had a blanket here was because there was no practical way for me to prop this thing up so that the camera could watch it. Oh, I'm sorry, 382 meters. I got a barometer app going on right here. Okay, so, and I'll just let that play while we're going on. The point is, a higher pressure should try and escape by all means necessary to a lower pressure. Okay, that's also why when you are in a submarine, you obviously want your submarine to be of very high quality, because the higher pressure is trying to get to the lower pressure on the inside, therefore trying to crush it. Okay, that's just what that does. But that happens only greater as you go deeper. Now the same thing with air pressure. As you are closer to the to sea level, okay, which is where I think it's 14 point whatever, 14 point whatever psi. As you go up in elevation, you know, your ears pop and all that other stuff, and you know, all that neat stuff that happens when you go up there, or when you go up in a plane and your ears pop. That's because the pressure outside is reducing, so therefore the pressure around your head is reducing. Okay, and there's a little tube that's back there in your inner ear and stuff, and that's what makes it pop because of the pressure change. Now you'll see that I'm driving up here. You can pay attention to right here. This is the elevation that I'm at, and all I'm going to do is I'm just driving up here. Now, like I said, the air that was contained here was at the pressure that I had when I was parked. But as I'm going up, you're noticing that the balloon is starting to fill up. Okay, and I also made sure, even though, well, you can't really see it here, but I made sure that I didn't. I had my windows cracked so that no pressure difference was created by the car itself. And up here you can kind of see it, but really you can't. There's at one point you can see it, but up here you'll be able to see on my tablet that that my sunroof is cracked. I just wanted to make sure that, you know, the air around me was also the air pressure inside of the car. Okay, this is simple stuff. Okay, this is simple experimentation. Now, according to you, and according to all flat earthers about this, who like to argue the contained atmosphere thing, according to all of you, there shouldn't be any change in pressure as you go up, because we're in a pressurized system, you know, in a container, as you are claiming. But I'm sorry, that's actually not a fact. Okay, pressure is caused by a force pushing down towards the ground, towards the center of the earth, by gravity in this case. Pressure is created by those things actually pulling it down. That's why it's not going off into space. Okay, this is happening at the molecular level. Okay, and that's why when you go up, the higher you go up, like if you go up to the top of Mount Everest, you know, even the oxygen levels are so low that you can only move like a couple of feet before you got to take a break. Okay, that's why it's such an excruciating thing. If not, people would be riding their bikes up there. Okay, it's pretty simple. And what do you call it? So, as you can see, the balloon's filling up even more. This is air that was at the pressure at the parking lot, okay, which is trying to escape because it's expanding. And because of the fact that I have a flexible balloon at the top, it fills up the balloon. This is this is easy stuff, and I don't know why all of you just don't get this. Okay, and I realize, but I mean, I understand why you're not allowed to get it. Okay, I understand that you're not allowed to get it because you're not allowed to believe in gravity. You're not allowed to believe in gravity because gravity would make the Earth round. You're also not allowed to believe in gravity if you're a religious person in the flat Earth community because of the fact that the creation of the Earth having to do with gravity obviously contradicts the creation of Earth by God. Okay, so that's just it's so I mean, I just don't even know where to begin with. I mean, this is stuff you can do yourself. You don't need to make a bet about it. Okay, this is silliness here, absolute silliness. Okay, because what you are denying is the very thing that we all experience. You know, we all experience this drop in pressure as you go up, and there is absolutely no excuse for a drop in pressure as you ascend without gravity. See what I'm saying? No container, no pressure. Yeah, keep thinking that, man. So let's see. And I'm about halfway up the hill now. So let's see. Do I have any flat earthers in here that don't understand this? That's right, Barry. That's my anti-theft stick. Hey, Critical Think. What up? Oh, I'm sorry, Mad Cynicist. Where was I doing flat Earth here? I'm debunking the claims of flat earthers. This was not about the Earth, even though it is about gravity. So technically, it is about the Earth. So deal with it, buddy. About halfway up the hill now. What? No other flat earthers? So let's see. Do I have any flat earthers in here? What do you mean pressure is pushing on the container from where? I don't understand what you mean by that, Shane. Pressure is not pushing on the container. As a matter of fact, the air was compressed as I was in the parking lot. I put a balloon over the top of it. As I'm going up, the pressure is decreasing. So therefore, it is the air inside is expanding, trying to escape. So the same gravity that's allowing them to rise is the gases that keep them stuck. Nothing about that sentence made sense, man. So the same gravity that's allowing them to rise is the same gases that keep them stuck around the Earth with a gap of about 100 kilometers? Nothing about that made sense, man. Oh, I caught that the other day on the one that somebody pointed to me, that Ranty is actually saying that Flat Out Hero did not specify paper charts, so therefore he did win. But, you know, flat earthers don't pay out because in the same breath, Ranty specifically said that you should never give in to what flat earthers say. Or should never give in to what a globe says. Show me your edge, vacuum. What edge? Do you see me going through a do you go through a container wall when you descend in water? John Sharp? The atmosphere, who said it was attached to the Earth? It's drawn to the Earth, dumbass. There's a gap of 100 kilometers in between. 100 kilometers where? Where is there a 100-kilometer gap in the atmosphere? You have about 2 minutes to tell me. Probably shouldn't have told you that because now you're just going to kind of talk around it. Okay, well then don't answer me. I mean, what else am I expecting? Why would that be a gap? He says a gap in the atmosphere. Oh, he did it on paper charts earlier today? Fucking cool.
Wonder what that guy's on about a gap. Who knows?
Yeah, I know. I was listening to that.
What gap are we talking about there, Mad, whatever the hell your name was?
There you go. I think the point's been done.
Yeah, I think the point's been made with his little balloon.
Yeah, he's just reacting to the chat.
Right, because you see vacuums, even though the vacuum
I think he drives back. I think he drives back down the mountain too, and it goes back down again.
Yeah, well, we know. Yeah, we know that's going to happen. Yeah. So for me to get it straight in my head, so right. So when he sealed the bottle with the balloon on it, he's sealing it at whatever it was at the car park. Let's just say, for argument's sake, it is 14.7 psi. When probably isn't, because that's at sea level, right? So as he's going up, so obviously the pressure's decreasing. So the pressure inside the container is still at 14.7. So therefore, there's a difference in pressure. So technically speaking, there's a greater pressure inside the bottle.
Yeah, the pressure inside the bottle increases.
In turn, yeah, hold on. So then, in turn, it inflates the balloon, right? Mm-hmm. Have I got that right?
Yeah, you're right so far. Yeah.
Mm-hmm.
Yeah, that's it.
Oh, okay.
So it's the pressure differential, isn't it? I'm just trying to get it straight in my head. So.
Delta P, it's called.
Yeah, exactly.
It's the same reason why water boils at a lower temperature at the higher elevation you go.
Yeah. I understood that as well. That's the laws of thermodynamics.
Kristen Frost Laserbeam asked an interesting question too. I haven't had a chance to think about it properly because I've been reading other things and doing other things. Her original question was, I'd have to find it again now. It was something to do with, she calls it, I'm just calling it fizzy drink because it's soda. I call it soft drink. What was the original question? I think I stuffed up the answer. So I can deduce from this that soda or soft drink fizzes more in lower elevation or higher elevation. Now if you work through it and think about it, if you've got less air pressure pushing down, if you're talking about an open bottle or a glass full of, like you fill your glass up or you open the bottle or is it already open, I don't understand what she means.
Sealed bottle.
Yeah, I don't know what she means.
I think she means a seal.
And when
I
think
that what she means is that So what she's saying is that if you opened a bottle of pop at sea level at 14 psi, and then opened it again at a higher altitude, so you say for example just 5 psi, would there be at the higher altitude less or more bubbles?
I'd say it'd bubble more because there's less air pressure outside for the contained bubbles, the nitrogen or whatever they use inside the liquid to escape out of the liquid, so that it'd escape out of the liquid a lot easier because there's less air pressure outside of the bottle. It'd be similar to the balloon and that other balloon expanding. Things will want to expand. That's how I'd think
of it.
What
would Stingray or Professor?
There'll be a lot more. Well, there's more pressure. An aircraft cabin is 11 to 12 psi compared to 14.7 when you actually did it. So, therefore, you've got a lot more pressure built up inside. So it will be more fizzy and it'll go a lot more.
Yes, it's a
higher altitude.
Yeah,
the altitude doesn't matter. You're in a pressurized cabin, so it wouldn't matter.
No. I think forget the pressurized cabin. What you're saying is, just say, for example, you climbed Everest, right? Just for example, you open that bottle of pop at the peak of Mount Everest compared to what it would be at sea level. What would be the difference? Would there be more or less more or less fizz?
Oh, shitloads more.
You've got a high difference in pressure.
Yeah,
there is a video of a guy doing that exact experiment, and basically when he opens the can up on the mountain, it's like opening a can that's been shook up. So even without shaking it
he ends up wearing it.
Yeah, he ends up wearing it because it's a lot more energetic when it comes out because the gases are trying to escape a lot quicker.
Oh, right, okay.
You've got a higher delta P. You've got a higher difference in pressure.
So what pressure would be inside a bottle of or a can of pop then? An average, anybody know? What would be the pressure inside it?
I don't know, but I suspect it's probably not a lot more than atmospheric.
Just give
me
a moment.
Probably say 20 psi or something.
Yeah,
so yeah,
you've got to remember,
so it's going to be
a lot of it's dissolved in. A lot of it's dissolved into the liquid, so there is a slightly higher amount of pressure, but it's when that pressure is released, that little bit of pressure is released, that the gases that are trapped within the water or the liquid itself, they become released as well.
It also depends on the temperature.
See, because you've got so you've got a higher pressure differential, so it's going to want to come out quicker compared to sea level. Right,
so I've got some figures here for you. So at room temperature, 25 to 30 psi inside the average soda can.
All right, okay.
Sorry. A refrigerated is 20 to 30, but a room temperature can run as high as 50 to 60.
Oh wow, okay.
That's because obviously temperature creates a huge difference there.
Yeah. So what you're saying is it's about the average that a tire could be from a car to a truck.
Yeah. An average car would be around about 25, 30 psi, wouldn't it, give or take?
Yeah, roughly speaking. And then your truck will go up to anywhere between 40 and 50.
Yeah.
My car's at 36. My motorbike is appreciably lower.
Yeah, I
remember off the top of my head.
I run my 4-wheel drive at 40 because it gives you a better fuel efficiency on the bitumen. But if I take it off road, I drop the pressure down to about between 25 and 30. Unless it's
we used to run our dirt bikes at about 10 or 15, but they had rim locks, so because otherwise you run the risk of your tire coming off.
This might be a bit trickier to work out. I don't know. I haven't thought about it yet. I just thought of the question first. I was thinking about it being like beer, probably be the same as soft drink. If it's a warm can of soft drink or a warm beer, when you open it, it can fizz more. But if it's a cold can of beer, it doesn't fizz as much when you open it. How does that affect? What's the atmosphere affecting it that way?
It's the energy from heat. So the energy that's inside the can, as in heat, allows everything move more.
You don't think it's to do with the molecules are contracted because it's colder?
Well, you don't look at it from the point of view as contracted, Terry. If you look at it from the point of view that hot atoms are moving more than cold atoms.
Which they expand.
But when they're hot, because they're moving more and they've got that potential energy within them.
An easy way for me to think about this, and someone correct me if I'm wrong, is because when you think about heat, you're actually thinking about movement. And when you're thinking about pressure, you're thinking about the inhibiting that movement. So when an atom hits something else and there is a kinetic stop there, that's pressure. So it's the same as if we're moving through the atmosphere now. The pressure is all the collisions that we're feeling with the atoms that make up the atmosphere.
Right.
So heat makes them move around. Thus, inside a container, when you heat it, they're moving around. All you're doing is you're creating more of that kinetic energy, which is increasing the pressure.
Right,
So
okay.
all of this fits in with, when it's cool, there's less movement, so you're actually dropping the pressure in there.
Yep.
When you heat it up, there's a lot more movement, so you're increasing the pressure in there because of that.
The colder it is, the lower the pressure.
Yeah.
So basically, so if heating a gas, all it's doing is just making the molecules move around a lot faster.
Yeah, that's it.
So when it gets to a certain temperature, wherever gas it might be, I'm sure it's different with each gas. I'm sure you get to a point when it freezes. Essentially, that all the molecules will stop moving. Right? No.
Say that again.
So I'm sure if you got the gases to a low enough temperature, the molecules will stop moving, right?
Oh yeah. So yeah.
So you're essentially freezing it.
Yeah.
That's why I spent years designing boiler rooms for gas pressure reducing stations dotted all around the country, because you run the gas in the main network at a very high pressure, too high pressure for your boiler in your house to take. So you have a station that reduces the gas pressure, and when you reduce gas pressure, it gets cold. So you have to heat it back up again, because otherwise, during the winter, everything will freeze up solid.
Oh, damn! I've just realised something. I had a constructive contribution there, and I'm in flat Earth mode today, so I should have just gone. Cool story, bro. Cool story.
But yeah,
are you doing this to try and model your flat Earth map?
No, I do. No, I do it. I do it. Yeah, you've never touched it, farmers. Sod off. No, I do it sometimes because I think it's the problem with flat Earth now is it doesn't actually, if I can argue better for flat Earth than a flat earther, then I can create, intellectual stimulation a lot more than a flat earther can, because a flat earther will just say something that's absolutely ridiculous, where at least I will try to ground it in reality and try to ground it in physics.
Yeah, I've got you.
Yeah.
And if I can argue better than they can for their cause, what's that say about their fucking cause when I'm against it? That's a bit weird, isn't it?
Yeah.
Quite.
Peter, have you listened to this to see if it's okay for sound?
Yeah, it should be fine, Terry. In particular, go up to about the halfway mark. Yeah, forget all that. And no, just before all that starts. Just back a little bit. There, go there. Oh, we can forget about all the aeroplane stuff because we've seen that many times.
Altitude was. So we're going to create a barometer that you can use in your home or your classroom to measure the barometric pressure. And we use just a few simple supplies. We've got some little jars. We've got one big jar, which we'll use here in a little bit. We've got balloons, straws, or you can even use toothpicks, some rubber bands, and a little bit of glue or tape like we're going to be using.
All right, so the first thing you ladies need to do is cut off the top of your balloons. All right.
Oh,
now,
just
next thing we're going to do is
good balloon.
stretch the balloon out here. Yeah, put it over the top of the jar.
Looking back handles.
Okay. Now take a rubber band and let's seal that on there. Good.
You need to learn how to stretch rubber over a round object.
Well, they're not using lube, Terry, so they're doing it wrong.
Oh, come on. Let's not lower the tone here.
What? I didn't say anything. I didn't say anything.
I was suggesting that they needed lube for sealing it. What
Oh.
are you thinking? What are you thinking,
yeah, what are
Casual?
you thinking, Casual? I'm just talking about stretching rubber over a round object.
Yeah.
The jar that's the same as out here in the room. That'll be important for later.
And now take your straw, and if you want, pass me a piece of tape. We're going to tape the straw right about in the middle.
Put the end of your straw right in the middle of your balloon in the middle of your jar, so that it hangs out over the edge. That's going to be our indicator.
All right. Now these are going to be used to measure the pressure outside, and it's going to take a little while. So
we have a demonstration here to kind of speed that up.
For a second, Terry. Just so everyone knows, this is actually designed for Year 9 physics. So ninth year of school physics type of
Year
thing.
9, that puts you at what, 14?
About 14, yeah.
Right, with you.
So we're going
Those
back
kids
to
look a
year
little bit
9
younger
or
than
10
14.
physics to try to get through to these flat earthers, how pressure gradients and things work.
However, Terry,
It's going to be a bit advanced for them.
Yeah, it's completely simple, and they might get it. But anyway.
Yeah, right.
Bye.
So the first thing that we're going to do is we're going to take another balloon and stretch it over the top of the jar. All right, so here we've got our balloon. We're going to stretch it nice and tight right over the top. Now we are going to push down on the top of there, and something's going to happen.
Now watch
Let's see what happens.
happens. So go ahead and push down.
Give it a good push with a couple fingers.
There you go.
You see what it's doing?
So you guys see what it's doing now?
Pull your fingers up.
Okay.
Push down.
Okay, so push down. So this is high pressure. This pressure is pushing down and it is raising the straw to show the higher pressure. What happens when you pull it up?
The balloon inside comes up.
You're using low pressure to lower the straw.
Yep. What we're going to do is we're going to take this back to our office, we're going to set it outside and look at it over the course of a couple of days and see how the barometric pressure changes. Should be pretty cool.
Yeah, that's about you, Terry. If you grab that second video that I popped in there as a follow-up to that one. Too many tabs, Terry.
Yeah, no, I don't think I've got it.
No, it's the one just above where Stingray said his thing.
Okay, so we are at the bottom.
Pressure and altitude, Boyle's law.
Yes, this is now this one's designed for, shall we say, just a little bit more advanced because it does bring in Boyle's law and all of that type of stuff into it, but just let it play. It kind of explains itself anyway. It's
bottom of a gondola at the minute, and we're going to do a little experiment about atmospheric pressure. So there is an awful lot of air above us, a fluid, which is weighing down us, and that causes atmospheric pressure. The higher we go, the less air there is above us, so the less weight is acting on our surface area, so the less pressure there is. So we've taken these balloons up there. This green balloon had a circumference of 70-ish, 66 centimeters at the base, and the pressure on our iPhone 6 was?
It was 850.
850, and it's already 840.
I was worried about the music playing.
110 hectopascals. A hectopascal is 100 pascals, and a pascal is a Newton per meter squared. So that's the unit we're measuring in. Too much physics.
Too many names.
Too many names. It's my balloon in a minute. We'll measure it when we get to the next section. So we're at 2,000 meters now. At the bottom we're about 1,600. Spectacular glacier behind me. And the pressure is now 770, so it's 850 at the bottom, 770 hectopascals. And here's my balloon, which now has a circumference of 69 centimeters. Okay, so this is a pretty good experiment. We're only at the middle station though, so we're going to be going even further. One reason is to get better views. More views, please. Like, share and subscribe. And another reason is to see if this will go even further. A really good example of Boyle's law, which is a law that Robert Boyle found in the 1600s. Okay, Boyle's law simply states that pressure and volume are inversely proportional. So higher pressure, lower volume, and lower pressure, higher volume. And that's what we're finding here. We're in the second stage of the cable car now, and we found that our balloon is still expanding, our pressure is still dropping. Okay, although we're not directly measuring the volume, we're measuring the circumference, we could infer the volume from that. but I'm not going to do the analysis now. So if I say pressure and volume are inversely proportional, that means if I double the pressure, I've halved the volume. If I triple the pressure, then the volume is a third of what it was before. I hope that makes sense. This has been Guerrilla Physics, where I'm all about you understand your physics more, so that you enjoy physics more, so that you get more confidence and you do better in those exams. Well, that's the snout of the glass, yeah? Which is the ice of it.
Yeah, that's about it, Terry. So, yeah, the last one, he just goes over the same results and they all pop their balloons. I hope that helps.
Well, it's just another demonstration of the higher you go in altitude, the more the balloon will expand. Dora said ignoring the temperature drop with height. I don't know. I think we're running out of videos, I think, for now. We've been going for a while. Going for nearly 3 hours. Stewie says, I need a new keyboard, the letters have worn off.
I could find more, Terry, but like realistically, we'll just be rehashing the same stuff anyway.
Yeah, I don't think we need any more videos.
I think it was a good one. Actually, you stuck to this, stuck to topic pretty much most of the way through.
Well, it's trying to find the proofs for the pressure gradient, which is
well, I think we have,
balloon,
haven't we?
the balloon. Yeah, the balloon is one of the greatest proofs you can show physically.
Yeah.
The pressure gradients.
Yeah.
Yeah, stuck in Florida. We showed a bit about
shows.
the chips. We already showed that one.
Slides was the best one as evidence for pressure gradient. So I think that's a good one, and we've talked about it, and atmospheric pressure as well around a fake Earth, that kind of stuff.
Well, I haven't even got to airplanes yet. To when an airplane's up higher in altitude, to notice that there's a difference in air pressure. Why airplanes are pressurized? So we haven't even got to that.
Yeah, as soon as you get past 10,000 feet.
Yeah, it gets a little bit more difficult to breathe.
Yeah. I wonder why.
Yeah.
And what would happen to an airplane if it wasn't pressurized at a higher altitude?
Well, just what I've said, you find it difficult to breathe.
Besides your breathing, just the actual physical airplane. Would anything physically happen to an airplane, or the airplane?
No. I've heard that they expand.
I've heard that they expand or contract. An airplane can at higher altitudes. The actual physical.
Yeah, there will be a certain amount. They allow for a certain amount. Yeah, tiny amounts. Yeah, of course there would be, but that's the main reason. But the reason why they have it,
the craft itself would be okay. It's the occupants.
Yeah.
It's not the craft itself.
That's the if you go back to the times, if you go back to say the Second World War, you had high altitude aircraft on both sides, and until the very end of the war, they weren't pressurized. So when you watch a film like Memphis Belle, when you see them all clonking around inside the plane and they've all got multiple layers of clothing on, most of their gear was electrically heated because they were in an unpressurized aircraft at sort of 25 to 30,000 feet. You were getting temperatures of -30, of -40 degrees C. And if you touched the aircraft with your bare hands, you stuck to it.
Yeah.
That's the problem. That and the fact they had to keep their masks on to get an air supply, so that when you had, say, the engineer had to move around and somebody said, look, I'm running out of ammo, can you get me some more ammo? You had small bottles of oxygen so they could unhook themselves from the air supply and move around inside there. It's all that sort of thing. It's doable, but it's physically dangerous and complicated. So yeah, you could fly if you had a heated suit and then your own air supply, you could fly an unpressurized aircraft up to 40,000 feet if you wanted, but it wouldn't be very comfortable.
Yeah, I mean, even with oxygen, even with that altitude, you still find it difficult to breathe because of the pressure on your lungs.
I think you'll find that the U-2 spy plane had an unpressurized cabin.
All right, really?
Yeah.
If I remember correctly, the pilots basically wore spacesuits because the cabin was unpressurized.
Yes,
I think.
Okay.
I'm fairly certain you're correct there, Farmer's Boy.
Yeah, I think a lot of that was down to sort of saving weight, because as soon as you start pressurizing, doing things like a pressurized cabin, you're adding weight, and that was, to all intents and purposes, a jet-powered glider.
I will correct you on the bombers slightly. I don't think you'd find a bomber in World War II that would have gone beyond 25,000 feet. I don't think. I think you said 30,000 feet.
Well, okay, whatever. Just off the top of my head, it wasn't until the B-29 came along.
Yeah.
The B-29 was pressurized.
Yeah. Which
but if you took something like a B-17, I mean, what was it? Let's have a look. What was its?
Oh, poor Professor Phil. Professor Phil, do not listen to Pete Shea. Unless you walk in there with a litre worth of vinegar and a litre worth of virgin olive oil, you are not going to be able to swallow anything he says, and it will all be about Aristarchus.
And wear face palm protection.
Here we go, Spaceman. The specifications for the B-17G, which was the last version of the B-17 bomber, it had a service ceiling of 35,600 feet.
Yeah. That was the pressurized, wasn't it? At that point.
No,
wasn't it?
Don't think so. No, the B-29 was pressurized, but I'm fairly certain the B-17 wasn't. And it was only, I think, on the G model that they actually sort of put glass over the waist gunner positions, because prior to that it was completely open. They didn't have any glass in them. It was just a hole in the side of the plane with the guns.
Yeah, I know it was. Yeah, but I'm fairly sure they didn't really go much above 25,000 feet in the unpressurized. But like I said, no, okay, if that's what you're reading.
But yeah, they had air supply. They had because I've read. How many books have read?
But wouldn't it? I mean, wouldn't it? When you start getting to like 30,000 feet or more, wouldn't it? Even if you had an oxygen supply, wouldn't it be difficult to actually breathe, even with an oxygen supply, because of the pressure on your lungs? You still find it'd be pretty uncomfortable, wouldn't it? In an unpressurized cabin.
I'm fairly certain there was ways and means, because they were using like a stylized spacesuit of. There's ways and means.
No, but Peter. But what we're talking about is, go on.
I was just going to say that in particular the plane that we were talking about before, they were doing things along the lines of pressurizing the suit around the legs.
Yeah, but they not what we're talking about is
that's a G suit. That's to do with maneuvers.
We're talking about World War II. World War II planes here, where it was all open, it wasn't pressurized.
Ironically, the B-29 that was completely pressurized had a lower service ceiling than the B-17. That wasn't.
Well, the B-17 might have had an operational ceiling, but that doesn't necessarily mean they were flying at that altitude, though.
Well, all I'm going by is its service ceiling, and the B-29 has a service ceiling 5,000 feet lower.
Strange.
How bizarre.
But I still like that clarified though. I mean, you're going to get to a height where, regardless whether you've got oxygen or not, you're going to find it hard to breathe.
Yeah, that's what I was getting at before. Casual, they actually used those pressurized the G-style suits early off to limit the amount of blood that was going to the extremities. Not so much for
that was.
Yeah,
That was fighter pilots.
Yeah, but they weren't doing it.
But not World War II bomber crews though. They didn't have G suits.
No. World War II fighter pilots.
That's what I'm trying to figure out.
G-suits.
Yeah, but that's what I'm trying to figure out. That's what I'm saying to you. Yeah, how would the World War II bomber crew in an open, an unsealed, unpressurized airplane get to 35,000 feet and not find it hard to breathe? That's what I'm trying to say. They didn't have G suits. Pretty sure of that.
Why would they need G suits? The G suits is only there to stop the blood going to your extremities in high G situations.
Yeah, I know. Yeah.
And only fighter pilots experience that.
I'm not arguing with you, Pete. I'm just trying to figure out how that would be possible. That's all I'm saying.
How it would be possible, or why they would do it.
How it would be possible at that altitude. Like I said, even because of the pressure on your lungs, it's regardless whether you've got oxygen, you're breathing oxygen. Surely the pressure on your lungs would be so great that you wouldn't be able to breathe wouldn't be able to breathe that oxygen.
You've actually got less pressure on your lungs, for starters, because
the higher you go,
the less pressure you've got on your lungs. They're breathing close to near pure oxygen, going straight into a mask, straight into their face. And the only reason, the reason that it was once explained to me, the reason why they added pressure to the extremities of their body was because they did have less pressure on their extremities. It was to stop the blood pooling in the extremities with the lower pressure. It would force the blood back into the main cavity of the air of the body.
Oh yeah, I'll get that bit. Yeah. Okay.
Yeah, but that was caused from the G forces imposed on them under high speed maneuvers.
I'm fairly certain. I'm trying to find it right now, but I'm fairly certain it was in the U-2 bomber.
Well, I've just looked up the U-2, and apparently it had a partially pressurized cabin.
Yeah.
So they still had an almost but not quite spacesuit. It was similar to a spacesuit, but it wouldn't have served in space. But it sort of assisted. They couldn't fly it without anything at all because the cabin was pressurized to an equivalent of 28,000 feet, which you couldn't survive in for very long. So they still wore a suit that
was a
maintained their life support, and it also catered for them in case they had to eject, which of course one certain individual did.
Yeah, it was a pressurized personal suit though.
What, in the U-2?
Yep.
Oh yeah. Because the cabin was only partially pressurized, so they still had to wear something. But I think the thinking was that it wasn't as expensive and heavy as fully pressurizing the cabin. Plus, it also protected the pilot in case he had to bail out, which of course Francis Powers did. Because although they believed that it flew too high to be shot down, they were never 100% certain. And of course, Mr. Powers found out the hard way that yes, indeed, the Russians could shoot one down because they shot him down. Then locked him up for a couple of years. I believe they even did a film about it fairly recently.
Yep.
Bridge of Spies?
Yep.
All to do with the negotiations of, look, if you give us one of our guys back, you can have him back and blah, blah, blah.
Yep. Seen it.
I've got his book on the shelf somewhere. It's quite an interesting read. But the U-2 was, they thought it would fly too high and they could fly over Russia with complete impunity because they didn't have a missile with enough range to shoot it down.
Yeah.
Until they shot one down.
It was also depicted in that film about the Cuban Missile Crisis as well, because it's around about that time, wasn't it? Yeah.
Yes, because that's how they found out. That's how they got the photographic evidence. They sent U-2s to fly over and go, oh look, you've got nukes.
Yep.
But the G suits that fighter pilots wear for a totally different
Yeah,
thing.
no,
When you put it into high G maneuvers,
yeah,
it tends
I'm
all the
not
blood flows
talking
to the
about
wrong places.
I'm not talking about the G suits. So
Hmm.
just reading about it right now, there's two main types of pressure suits. Ones that give direct pressure and ones that give indirect pressure. Direct pressure would be things like the suit itself being tight around that area of the body. Indirect pressure is by filling the suit itself with a compressed gas. Direct pressure suits themselves, generally speaking, are the ones that we're talking about for G suits.
Yep.
The indirect pressure being the ones that are pressurized are the ones that they used in the U2. But the indirect pressure also fall into two groups, which are partially pressurized and fully pressurized. The partially pressurized suits pressurize certain parts of the body. That they can they can only provide protection up to certain altitudes. They do not provide protection for extended periods of time at low ambient pressures.
Yeah, that makes sense. Oh, later, spaceman.
Oh, okay. Spacey had to go.
Yeah. Yeah, St. John's.
Hey, Terry.
So don't go up high if you need to fart.
I was just looking at trapped gas will expand dramatically as altitude increases.
You know what my camera's doing at the moment, don't you?
Working?
Yeah, it's outside working. So, okay.
Yeah, I couldn't find any more about
the
that.
physiological deficient zones extend from 3,600 meters, which is 12,000 feet, up to 15,000 meters, which is 50,000 feet. There is an increased risk and problem such as hypoxia, HYPOXIA.
Oh, hypoxia.
Thank you.
Yes. Yeah, that's something that people who climb Mount Everest
exactly
are in great danger of suffering from. Yeah.
Trapped gases. Where gases trapped in the bodies expand.
Yeah.
So, like we were talking about before with the balloons, the same thing can happen in the human body as we go up into the upper atmosphere, which is almost the same as the bends when someone that's done a deep dive comes up too quickly through the different levels of the sea. And basically the dissolved gases such as nitrogen may form in the tissue, causing decompression sickness. Above 10,000 meters. Yeah, above 10,000 meters, oxygen-rich breathing is required to approximate the oxygen available in the lower atmosphere, obviously, because it's under heaps more pressure, so you've got more available oxygen in the air that we breathe down on land. While above 12,000 meters, oxygen must be under positive pressure. Above 15,000 meters, respiration is not possible because of the pressure at which the lungs excrete carbon dioxide.
What was that? 15,000 meters.
Yeah, above above 15,000 meters. Approximately.
Yeah, those B-17 crew were flying at about 10,000 meters maximum. So
yeah, so at approximately 87 millimeters of mercury, exceeding outside air pressure above 19,000 meters, also known as the Armstrong limit. Fluids in the throat and lungs will boil away. Generally, 100% oxygen is used to maintain an equivalent altitude of 3,000 meters. So there you go. Anything above 62,000 feet, anything above 19,000 meters, the liquid in your throat and lungs starts to boil.
Yeah. Nasty.
See, and that's not even. What did they change the height to? It was 100 meters. 100 kilometers, wasn't it?
Oh, what, the Kármán line?
The
Kármán
line.
In space.
Yeah.
Yeah, something like that. Yeah. So it's sure, you're still well within Earth's atmosphere. There's just nowhere near enough of it. There's just not enough pressure. Which at the end of the day is all the vacuum of space is. It's a lack of pressure. Well, you only have to look at how much trouble people get into going up Everest, and that's a fraction of it. Unless, of course, you're a Sherpa who's been living up that way all his life and is adapted to a lower pressure. Not that low, but a lower pressure. So there you go.
Yeah, I was just reading at what the highest altitude planes have actually flew at. Been two, but there's two different reasons for why they're different.
Which two are they quoting?
In '62, American test pilot did a altitude of 314 feet, but a Russian pilot did it in 1977, and he went to only 123 feet. He was given the record of the world altitude, but it's the way the two aircraft were launched puts them in different categories. The X-15 was never intended to take off under its own power. It was carried aloft by a modified B-52. So White's record fell under the altitude gain airplane launched from a carrier category, and has since been broken by Michael Melville during his June 21st, 2004 Spaceship One flight.
Oh yeah, yeah. If you want a good example and a good idea of the X-15, watch the start of the film, The First Man, all about Neil Armstrong, because it starts with him flying his X-15 mission, and he actually skips on the Earth's atmosphere. And the X-15 had two forms of control. You controlled it as an aircraft, or it had what they call a reaction control system, little miniature rockets so that when you was too high in the atmosphere and there wasn't enough air for your wings and tailplanes and everything to work, you could use rockets, and that's how he got himself back into the atmosphere, because he was basically out of control. He skipped off the Earth's atmosphere, and if he hadn't got the reaction control system, he'd be gone, and he would never have been first man on the moon. You know, it was he was out in space, and if it wasn't for those little control rockets, he would have gone. He would have done what the flat Earth keeps accusing all aircraft of doing. He would have carried on straight. He was technically in space, I think, by that point. He'd crossed the Kármán line and lost control. And it's very well done. It's quite a good. It's a good start to a film, you know. But it does show you, you know, poor bugger. You were sat inside the X-15, hung under the wing of a V-52, and they took you up to altitude and dropped you, and you lit the engine, and off you went at incredible speeds of sort of 5 or 6 times the speeds of sound. But that demonstrates very well what happens when you cross the Kármán line.
Demon Orb said bouncing off the dome. Yeah, he bounced off the dome.
Well, he certainly bounced, but he actually bounced off the atmosphere. He went slightly too high at maybe slightly the wrong angle, and when he went to come back down, he realised that his controls achieved nothing, and he has to switch over to these, what they call the reaction control system, little miniature rockets sort of in the wingtips and the tailplane or what have you, to sort of give him a gentle nudge back into the atmosphere. Otherwise, he'd have kept on going.
Terry, did you want to finish on a video, or have you almost had enough?
Yeah, I've got 15 minutes. I reckon we could finish off in about 15 minutes.
Well, it's funny enough. Kat's just dropped a video that goes for 14 minutes 33. I've dropped it in the internal chat.
Okay.
That's a happy happy happenstance.
Yeah.
That's too much of a
and
coincidence.
we all love a Conspiracy Cats video.
Oh
Yeah.
my word.
I mean, he's just so good at
I
it.
was just showing you a picture of that. I think it's the X-15. 'Cause that's the only one
That's
I
the
could find.
X-15, yes.
Yeah. So it's basically a rocket, not an airplane.
Oh, it is. It's a rocket plane.
Yeah,
it's a rocket plane.
Yeah.
Yeah. Like I say, Armstrong possibly flew it twice, I think.
Mippet says, Terry, who did you nominate for FDD in January? Just wondering. Sorry, Mippet, I'm still ironing out the bugs to work out how we're going to format that for each month or whatever yet. I got a new contender, but that new flat earther we found the other day. Yeah, that you had to get
Dunny Door.
Yeah, Dunny Door, that's him. I've got to put him in.
Oh, I don't know. I've got a feeling he's a poet, Terry.
I'll put a question mark next to him then. Well, yeah, but his name wasn't Dunny Door. It was
just give me a moment. Let me hit my history.
Yeah, I'm only
button.
just putting the names in as the nominees, and then we can go back to it later. I don't want to put Dunny Door in here, otherwise I won't know who he is.
Yeah, I'll have to scroll back through all the good videos that I've watched.
And I'll get yours ready. Conspiracy Cats.
You know, someone will say it out in the chat before I find it.
I know we call him Dunny Door or whatever. Yeah, forget his real name. Dunny Do or something, or
So it was something like that. Gonna do?
Gonna Do, that's it. The Gonna Do? Sounded like Gonna Do. I think it was Gonna Do.
I don't know. I keep scrolling through my my playlist, and I keep finding all these songs from Irish Stew.
Well, I'll put Gonna Do in. We'll figure it out.
Oh, Irish Stew. I went to get me bass today, but they didn't have one there that I like, so I didn't get one today. Just so that you know.
Oh, just out of interest, I just looked up Armstrong. He flew the X-15 7 times. And on that particular flight I was talking about, he reached an altitude of just over 207,000 feet. Oh, that'll be a Cats video then. Conspiracy Cats!
Have I got him shield on the shield your shit?
I don't think so, Terry.
But I keep forgetting who I've got to put in there.
Yeah, we need to get they. We need to
No,
get
I've
they.
already, no, I fixed it.
Did you?
Yeah. I've been adding the ones when I remember them into the bot. I thought I had Conspiracy Cats. I'll have to check the bot list and see who I've got. Next time I'm over on Discord, I'll check it out. Here we go. Are you ready for this?
I think so.
Oh, bring it on.
So how do you go about making the most ridiculous, scientifically illiterate challenge on the internet? Well, firstly, you need to find the two most scientifically illiterate people, starting with this man, Nathan Thompson, who believes that brain training can make your feet grow.
So, man, my feet are getting bigger. I grew 4 shoe sizes since I've started this program.
Oh, bullshit.
And then find someone like this guy, who knows what a spirit level looks like.
So this is what they call a level.
But who actually thinks it's a mobile phone. I'll show you what I mean. Hello? Yeah, what is it you want to see?
We want to see the physics of water finding and maintaining level being superseded by a theory called gravity.
No, sorry mate, I can't hear you. Something mustn't be working right. Anyway, together they have made the most farcical flat earth video that I have ever seen. Yeah, I know, sorry Ranty, but I am even including you in that. I don't think even you at this point could say anything that's more ridiculous than what you're about to witness.
Appears to be a second moon behind the full moon.
Actually, Ranty, that's not a bad effort. Anyway, Nathan Thompson and Flat Earth Millionaire have decided to offer $200,000 to anybody that can complete 3 of their scientifically illiterate challenges. Now, we all know Nathan Thompson. He's a flat earther famous for harassing scientists wherever he goes and calling them a liar. Most famously in this example.
Well, I just got kicked out of Starbucks for asking NASA employee questions because he's lying.
And most irritatingly in this example.
So, if you're lying to kids, the Bible says you should go kill yourself. Did you know that?
Now, perhaps unsurprisingly, Nathan Thompson is also famous for failing spectacularly hard whenever his own understanding of science is put to the test. Like the time when I was debating him about our observations of Polaris and how they disprove a flat Earth. Now, in this debate, I asked Nathan Thompson to explain to me how he would calculate the length of a side of a triangle. Pretty much no more than high school trigonometry. Now, despite the answer being on the screen, this is what Nathan Thompson said.
How would you calculate it?
I mean, so your argument is that the north, I personally can't calculate that. I don't work in kilometers. I normally work in miles.
Yeah, apparently flat earth trigonometry doesn't work if the numbers are given in kilometers and not miles, even if the answer is on the screen. Although, to be fair to him, I did ask him how you'd work it out, not what the answer was, but still, it was funny anyway. Now, that's Nathan Thompson. Let's meet Flat Earth Millionaire and find out how he got involved in all of this. Keep your eye out on the subtitles.
How'd this come about?
Yeah, well, back in late 2014, I stumbled across some early videos from Math Powerland, and within 30-45 minutes, I knew that the photos from space of Earth were faked. I knew that water doesn't stick to the bottom of a spinning ball. It's never been replicated. So I've been in the movement for quite some time.
So there we have it. The scene is set. 2 flat earthers, 3 stupid challenges, and $200,000. Hello?
Hello, it's me. Look, just get on with it and introduce the first challenge, will you?
Yeah, that's what I was just about to do. Let's find out about challenge 1.
What does the challenge consist of?
The challenge, there's 3 main parts. We want to see replication using the scientific method, you know, observing, measuring, and repeating water sticking to a ball. You know, it didn't even have to be spinning. We just want to see water conforming to the exterior of a ball, okay, without it dropping and dripping out off the bottom and sides.
Now, I have heard some ridiculous things from flat earthers. Like the time when I was arguing with a woman who confused the word fusion, as in nuclear fusion, with the word fizzy.
Well, if it's fusion, isn't that just bubbles of air in water?
Or when this flat earther told me water was alive.
I believe water's sentient.
But this first challenge really takes the biscuit, and we all know why. What they are asking us to do is perform an act that would actually disprove gravity as we know it. So my take on it is simple. Either number 1, you are that academically weak that you fail to grasp the simple concept that the gravitational pull of a ball on Earth will never overcome the gravitational pull of the Earth. Or B, you do understand that, in which case you are being deliberately dishonest. So what is it? Are you A, academically weak, or B, just massively dishonest? However, here's challenge 1 completed for you anyway, and I will wait for the inevitable accusations of how all these videos are fake.
Well, we're definitely scientifically illiterate, I'll give you that. Anyway, can we move on to the next one now, please?
Okay, well, let's see if you actually can move on to the next point. You see, we've done challenge 1. We know there are 3. So what number comes next?
Beautiful.
Okay, so we want to see that.
Have to be a big ball because of gravity.
Absolutely,
Right.
because of gravity. This
Okay.
theory that supersedes the physics of water finding and maintaining level.
Yeah.
Okay, it's
That
a theory.
supersedes the theory or law of thermodynamics.
Yeah,
that the
second law of gas yeah.
would escape into the vacuum.
That's the third.
All right.
That's the third challenge is replicate using the scientific method, showing where a vacuum or zero pressure can exist next to a pressurized system.
So in typical flat earth fashion, after challenge 1 comes challenge 3. I really can't help but think that these guys might really have benefited from rewatching Mark Sargent's Flat Earth Maths Masterclass from before Christmas.
1, 2. Three.
So anyway, back to the challenge. This whole vacuum of space next to our atmosphere thing is something that a whole lot of flat earthers seem to struggle with. They seem to think somehow it violates the second law of thermodynamics. A bit like this guy here.
All right, sweet cheeks, let's go. The vacuum of space is 10 to the negative 17 torr. That, my friend, is some serious pressure. But it's not, is it? It's almost no pressure at all. It's literally nearly zero pressure. Watch this next sentence. Next to a gas, and yeah, I'll not even bother finishing that one off because I'll have probably got it wrong anyway. We'll just leave it at that. And then entropy would happen with the second law of thermodynamics, so I literally have no idea what I'm talking about with entropy. It either increases or decreases. It just doesn't just happen, does it? Anyway, here we go. Gas is not a negative pressure. Bloody hell, I got one right, I think. A vacuum is, yeah, not absolute negative though. Someone's confused me along the line there with that. Oh, bollocks.
So given the fact that there's probably more chance of this little finger winning the men's 4x400 metre relay at the next Olympics than there is of Nathan Thompson or Flat Earth Millionaire actually explaining what the second law of thermodynamics is, I thought I'd challenge myself to see if I can explain inside 30 seconds a little bit about thermodynamics, entropy, and how our atmosphere is involved in that.
Absolutely can't wait.
Start the clock. The second law of thermodynamics says that in a closed system, when energy changes occur, entropy must increase. And at a very basic level, what that means is the energy just gets spread out a little bit more. Now, the Earth isn't a closed system, but still, let's crack on anyway. Here's the sun. When energy from the sun is absorbed by Earth, it is re-emitted, but it's re-emitted as a higher number of lower energy photons. So therefore, the energy is being spread out, entropy is increasing. And this process repeats itself as energy travels through the atmosphere from one layer to the next, absorbing and then re-emitting the energy as a high number of photons. By the time the gas particles get to what we would call the edge of space, they have done so much work against gravity and radiated off so much heat that they don't have any energy left to cause any sort of significant pressure.
Amazing.
Thank you. So, what that means is, as we all knew anyway, there is no high pressure next to the vacuum of space. It is a gradient that fades off to zero, and that in no way, shape or form contradicts anything to do with thermodynamics or entropy. Give us a second. Hello?
Oh, you think you're so smart, but we don't even need to understand science to say it's rubbish. We're flat earthers.
Anyway, let's see if that little explanation has helped out our commenter from before, shall we?
No, I don't think it has helped. In fact, I think I'm even more of a confused mess now. Look, listen to this. The container with gas pressure. I think you missed the word pressure. See what I mean? Then this is a good one. The put a vacuum doesn't suck or have pressure. That's why a space, not space, that's why a space is 10 to the negative 17th torr. Spoke wrong. If it's actually nothing, they should just say it's 0. See what I mean? I'm putting words together, but screw the order. That doesn't matter. This next bit's good too. Even the strength from 1 torr, what kind of torr is that? And atmospheric pressure will crush a rail car, right? So that will crush a rail car, but that isn't strong because you can crush a rail card just by looking at it. Oh, I really hope Conspiracy Cats doesn't turn this comment into a song and, you know, put it at the end of this video. I guess that didn't help him. Anyway, somebody else who still doesn't understand the second law of thermodynamics is Nathan Thompson. Now, you think somebody who was involved in a challenge where $200,000 were on the line, and the challenge was claiming that a violation of the second law of thermodynamics would have to happen for us to have an atmosphere next to space. You'd think somebody like that would have a basic understanding of what the second law of thermodynamics was. So I popped onto Nathan Thompson's channel while he was live streaming a couple of days ago, and I asked him.
Shut up before I block you. You're boring and annoying and scientifically illiterate.
So in other words, no, he's still pretty clueless. But that didn't stop me from continuing to ask.
Conspiracy Cat says, what's the second law of thermodynamics? Well, according to M. Stone, who got toe tagged on Nathan Oakley's channel the other day, it's the law that proves space is fake. Conspiracy Cats just repeats himself like a broken record. So Conspiracy Cats, adios muchacho. Oh, Conspiracy Cats came back on his other channel to get blocked from that channel. How dumb. What a loser. How did the Conspiracy Cat, wow, back on a third channel, asking the same question. Can you explain the second law of thermodynamics? Did I not explain that? There he is. Conspiracy Cat's patron. Can you explain the second law of thermodynamics? What? That's the 5th one. 5th channel. What a clown show.
So my take on this challenge is simple. You are either A, so scientifically illiterate and academically weak that you just can't understand that there is no high pressure next to a vacuum of space and it is in fact a pressure gradient that fades off to 0. Or B, you do understand that, and for some reason, when you're asking to show a high pressure next to a vacuum, you are being deliberately dishonest. So which one is it? Are you A, massively academically and scientifically illiterate, or B, hugely dishonest? Anyway, just to highlight how easy it is to demonstrate a pressure gradient, here's a bag of crisps at different altitudes. So what was the final challenge?
I want to see where sea level, where the physics of water finding and maintaining level, go from sea level being level and flat, a flat surface, to convex. We want to see where sea level turns to sea curve, okay?
Right, well I can help with that. Take your mobile phone and hold it up to the horizon.
Okay, you mean, what, just like that, yeah?
Yeah, well done. Now, go to the seaside and do that, and take a picture. These pictures, by the way, are from the Metabunk website, and I've linked that website in the description. Please check it out. There is so much flat earth destroying stuff on there. It's absolutely incredible. Anyway, once you've taken that photograph, properly analyse it. Zoom in a little bit, maybe compress it left to right a bit, and you'll see that the spirit level remains flat, but the curve of the ocean is more than visible. So challenge 1 and challenge 3 completed. Challenge 2 totally invalidated due to it being more stupid than even this.
What? Are these flames defying gravity by going up?
So I won't claim my money now, but I might let you keep it if... Well, if you decide to spend it on a ticket on one of the upcoming Virgin Galactic space missions. You see, from there you'll be able to see and film the curvature of Earth yourself. You see, it's all well and good to brag that you've got all this money to throw around, and it's all well and good to claim that you're searching for the truth about the shape of the Earth. But why don't you put the two together? What is stopping? Think about it. What is actually stopping you from buying a ticket with the same amount of money you've put up for this challenge to do something like that? What is actually stopping you? Nothing is stopping you. But I wonder if you'll do it.
No.
Exactly. Anyway, remember that comment from before?
Yeah, I think he means this one.
Well, to play us out, the Flat Earth community and I have been working together to turn it into something a little more beautiful. Enjoy. The container with gas pressure. Pressure. I think you missed the word pressure. So here it is again.
Press, pressure.
But a vacuum doesn't suck.
Beautiful.
Cheers. I thought it was too high for me, but I might have just got away with it.
Thank goodness.
Yeah, I know. Anyway, now let's just say something dumb about space.
This weight is space weight.
Not that dumb. If it's actually
nothing,
they should just say it's
Zero.
What a team effort. You guys are amazing.
You're the man, Conspiracy Cats.
Oh, thanks. I'm the man. I like that.
Black man or a white man?
Yeah, one of those two.
Anyway.
Yeah, you're right. Let's crack on with it. Atmospheric pressure will crush a rail car, but that's not strong, cause you can crush a rail card.
Shut up before I block you. You're boring and annoying and scientifically illiterate.
But you are Superman.
Superman.
Well done, boys.
Superman.
Alright, don't get carried away. You can't just throw it in at any old time. Anyway, I've had enough of this. Over to you, Nathan Roberts. You finish it off. Lovely jubbly.
He hasn't made one for a while, so it's good to see he made one.
He put a post up the other day, sort of said that I think he's coming back with a bit of a bang. So hopefully we'll see a few more yet.
He's such a talented man.
Yeah,
he is. I wish I'd had teachers like that when I was at school.
Yeah, I wish I did too. I wish I had teachers. That would have helped.
You mean teachers rather than just educators?
Yeah, whatever they were.
Indoctrinators.
I don't know what they were. Well, I think we've had enough for tonight. I think we've covered a lot of pressure. I don't know what's happened to Stingray and Pippet. Professor Phil.
Well, Stingray's lost his mic.
Oh, when did he lose it? Can't find it.
I don't know. He must have stuck it. He must have stuck it somewhere underneath the dome.
That's what you get for pretending to be a flat earther.
Yeah.
Yeah.
It's coming around to bite you.
Science stops working
Bite
for
you on
him.
the bum. Yeah.
Well, thanks you guys for hanging in there. I'll thank you, Peter, for hanging in there. I thought you were going to disappear.
I did, but the pill started kicking in. So.
Yeah, I was going to ask you if you got any drugs. That would have helped. So, I'll say our goodbyes.
Alright, see you YouTube.
I'm just typing in my goodbyes to all the people in the Peanut Gallery.
Goodbye and thank you to the Peanut Gallery.
Yeah, Mippet, Irish Stew, Skyfly Bry, Boggs. Who else is out there? Charlie, Dartman.
Your attendance is appreciated as ever. Especially as you had to wait for so long in the first place.
Yes, they did. I'm glad they're patient.
Yep.
I forgot to say a shout out to somebody last night, and I can't remember who they were. Oh no! Any of you guys out in the Peanut Gallery remember who it was last night that I forgot to shout out to? Right at the end, it was. I can't remember who it was now. They should know who they are.
Yeah. They might be.
Oh, and Casual's got back. Just in time for us to finish.
Did he? Oh dear. Oh, he can say his goodbyes then.
He's in Discord, Casual.
Is he? What emoji do I need now? That one? There we go. There we go. I've done me goodbyes out there. Oh, the Skyfly. Have you said everyone?
Yeah, I think so.
Stuck in Florida, Irish Stewie, Professor Phil, he was out there for a while.
Yeah, I think he's disappeared now, though.
Oh, he's still on here, though. He's going to get kicked in a minute. Charlie. Yeah, thanks, Charlie, for your interesting questions.
Yeah.
Yeah.
Calling bullshit.
Be pretty boring without questions.
I'm going to time that person out if they keep coming in here. Mippet. Oh, poor Mippet with the technical issues with the mic.
Oh.
Dear. We'll get there. We'll get there. Oh, GPS. I didn't see that. We're there.
GPS.
Aaron Armstrong. Boggs. Oh, Lokio. Unstructured understanding.
Where would we
did I
be with that?
think?
Kirsten Frost.
Oh, yeah, Kirsten Frost, laser beams.
Hit me with your laser beam.
Yeah, that's about it, I think.
Yeah,
Alright.
I'd say so. I was stuck in Florida. Was on there earlier.
Oh, were they? Yeah, I've seen that. Okie dokie then.
All right.
Bye, everyone.